What if reality isn't as clear as we think, but only a glitch created by our own minds? We believe time moves forward, but what if time never existed at all? Mass, space, motion, light, they seem like the core of our universe, yet they might just be shadows of something we can't name. This video will take you into the dark corners of physics, the edge of reason, and beyond what you've ever questioned. If calm, thought-provoking content like this speaks to you, I'd really appreciate it if you gave the video a like and subscribed. Now, close your eyes and begin to think. The flow of time. Reality's silent conductor. Imagine a universe where everything happens all at once, no past, no future, just a chaotic blur of events with no sequence, no cause and effect. It's impossible to grasp because at the heart of our existence there is time, the silent conductor orchestrating the grand symphony of reality. Unlike the physical objects around us, time has no shape, no weight, no form, and yet it dictates everything. It is the invisible thread weaving moments together, allowing us to compare the past with the present, anticipate the future, and define the sequence of everything that unfolds in the universe. But how do we measure something so intangible? Nature itself provides the answer. A second is marked by the vibrations of atoms. A day is carved by the Earth's steady rotation. A year unfolds as our planet completes its grand orbit around the Sun. These cosmic cycles give time a tangible presence, letting us break it down into manageable pieces, minutes, hours, centuries, so we can organize our reality. Yet, time is more than just a tool for measurement. It is a dimension of existence, governing the rhythm of life itself. It directs the dance of celestial bodies, orchestrates the tides, and fuels the unseen march of biological processes. Plants grow, seasons shift, galaxies drift, all under time's relentless flow. Without time, motion would be meaningless. Events would have no order, cause and effect would vanish, but as long as time moves forward, so does the universe, carrying us along with it moment by moment. And with that, let's explore the next foundation of reality, the essence of location. Every object in the universe exists somewhere, but describing exactly where is more complex than it seems. Position is the foundation of motion. It tells us an object's location at any given moment. But here's the catch. Position is never absolute. It only makes sense when measured relative to something else. In physics, position is defined using coordinate systems. In one dimension, it's as simple as moving forward or backward on a number line. In 2 dimensions, a point on a map gives precise latitude and longitude. In 3 dimensions, objects move through space with X, Y, and Z coordinates marking their exact location. But position isn't just a set of numbers. It depends on perspective. A moving train appears in different positions depending on whether you're standing on the platform or sitting inside. This concept, called frame of reference, is crucial in physics. The same object can have completely different positions depending on the observer's point of view. Beyond daily experiences, position is key to some of the most advanced technologies we rely on. It helps scientists track satellites, locate earthquakes, and measure tectonic plate movements. Whether studying the smallest particles or the vast expanse of space, understanding position is the first step in describing and predicting motion. Next, we explore distance, the space between 2 positions, and why it matters. How far have you traveled today? Whether it's a short walk to the kitchen or a long commute across the city, distance is one of the most fundamental concepts in physics. It tells us how much ground an object has covered, regardless of direction. Unlike position, which pinpoints a location, distance is a pure measure of length. Imagine a car winding through curvy roads. The total distance traveled isn't just a straight line from start to finish. It's the sum of every turn, detour, and stretch of road along the way. Even if the car returns to its starting point, the total distance remains the full length of the journey. In physics, distance is classified as a scalar quantity, meaning it has only magnitude, not direction. This is what sets it apart from displacement, which measures the shortest straight-line path between 2 points. For example, if someone walks around an entire city block, their distance traveled may be several hundred meters, but their displacement could be just a few meters if they end up near where they started. Distance is measured in meters, kilometers, and miles, and it plays a crucial role in both daily life and scientific exploration. It helps us navigate roads, measure heights, and calculate depths. On a much larger scale, precise distance measurements allow scientists to map microscopic structures, track planetary orbits, and even gauge the vastness of the universe. But measuring how far something moves is just one piece of the puzzle. What about the objects that are moving? What gives them their presence, their weight, their resistance to being pushed around? To understand that, we need to explore another fundamental concept: mass. Pick up a bowling ball in one hand and a tennis ball in the other. Instantly, you feel the difference. One is heavy, resisting your effort to lift it, while the other is light and effortless to move. What you're experiencing isn't just weight, it's mass, the very property that gives objects substance, presence, and resistance to motion. Mass is what separates the physical from the intangible. It's what gives everything, from the smallest subatomic particle to the largest galaxy, a measurable existence. Without mass, objects wouldn't have weight, they wouldn't resist motion, and gravity itself wouldn't function as we know it. At its core, mass quantifies how much matter an object contains, and unlike weight, it doesn't change. Whether an object is on Earth, the Moon, or floating in deep space, its mass remains the same. That's because weight depends on gravity, while mass is an inherent property, independent of external forces. But mass isn't just about lifting objects. It controls how the universe behaves. It dictates how gravitational attraction works, keeping planets in orbit, pulling objects toward the ground, and even shaping the grand structure of the cosmos. The greater the mass, the stronger the gravitational force it exerts. That's why stars cluster into galaxies, why black holes pull with such immense strength, and why the sun's gravity dominates the motion of our entire solar system. Even in everyday life, mass plays a role in everything we do. It determines how much force is needed to move an object, whether we're building a bridge, launching a rocket, or simply measuring ingredients in the kitchen. On Earth, we measure mass using scales that compare an object's resistance to gravity. But in space, where gravity is absent, we determine mass by how much force is needed to accelerate an object, a crucial principle in physics and engineering. Mass is more than just a number. It's the foundation of all physical interactions. It determines how objects respond to forces, how they move, and how they shape the world around them. But what happens when mass starts to move? How does it interact with the forces around it? To answer that, we must explore the next great principle of physics: motion. Even in absolute stillness, nothing is truly at rest. Atoms vibrate, planets rotate, and space itself expands. Motion isn't just movement. It is the very essence of existence, the force that shapes everything we see and experience. At its core, motion is simply a change in position over time, always measured relative to something else. A car passing by seems to be in motion to a pedestrian, yet to the passenger inside, it feels perfectly still. This reveals a fundamental truth. Motion is always relative. It only has meaning when compared to a reference point. But not all motion is the same. Some objects move in a uniform way, traveling in a straight path at a constant speed. Others experience non-uniform motion, where their speed or direction changes over time. A swinging pendulum, the orbiting moon, the rise and fall of ocean tides, each is a unique expression of motion shaped by the forces acting upon them. Motion can take many forms. Linear motion, like a falling rock, moving in a straight path. Circular motion, like a spinning wheel or a planet orbiting a star. Periodic motion, like a pendulum's steady back-and-forth swing. Chaotic motion, like the unpredictable movement of gas molecules. But no matter the form, motion is everywhere. It governs how objects interact, how energy flows, and how systems evolve over time. It dictates the patterns of nature, from the drifting of autumn leaves to the grand dance of galaxies. But how do we measure motion? How do we quantify how fast something moves from one place to another? To understand that, we need to dive into the next key concept: speed. Speed is one of the most fundamental aspects of motion, defining how quickly something moves from one place to another. Whether it's a runner sprinting across a track, a car cruising down a highway, or a distant planet hurtling through space, speed determines the rate at which distance is covered over time. At its core, speed is simply the total distance traveled divided by the time taken. It is a measure of motion that exists all around us, shaping everything from human activity to the movement of celestial bodies. Unlike velocity, which considers both magnitude and direction, speed is a scalar quantity. It tells us how fast something is moving but not where it's going. In our daily lives, speed influences the way we experience the world. From the moment we step outside, whether walking, driving, or flying, we interact with different speeds without even thinking about it. Some movements are slow and steady, like the gradual drift of clouds, while others are incredibly fast, like the shock wave of an explosion. But speed isn't just limited to things we can see. It extends to the scale of the universe itself. The Earth orbits the Sun at breathtaking speeds, and light, the fastest thing in existence, moves through space at nearly 300,000 kilometers per second. These speeds shape the very structure of the cosmos, determining how galaxies interact and how information travels across vast distances. But speed alone isn't enough to describe motion completely. What if direction matters? How does movement change when both speed and direction are considered together? To answer that, we must explore the next crucial concept: velocity. A car speeds down the highway at 100 kilometers per hour. It's moving fast, but that alone doesn't tell us much. Is it heading north, east, swerving through winding roads? Suddenly, it takes a sharp turn west, maintaining the same speed. The number on the speedometer hasn't changed, yet the motion has, because motion isn't just about speed. It's about direction, too. This is what separates velocity from speed. While speed measures only how fast something moves, velocity tells us both the speed and the direction. This makes it a vector quantity, meaning it has two components: magnitude, how fast, and direction, where to. If either of these changes, the velocity changes, even if the speed stays the same. Take an airplane flying at 800 kilometers per hour. It's not just moving, it has a specific velocity, determined by its heading. If strong winds push it off course, its velocity changes, even if its speed remains constant. The same principle applies to ocean currents influencing ships, wind altering the flight paths of birds, and even sports, where the velocity of a soccer ball determines its trajectory. In physics, velocity is key to understanding trajectories, motion prediction, and navigation. It's what helps us track planetary orbits, fluid dynamics, and the movement of particles on a microscopic scale. But motion isn't always steady. Objects speed up, slow down, and change course constantly. How do we measure these changes? How does an object's motion evolve over time? To answer that, we need to explore the next fundamental concept: acceleration. A car is cruising down the highway at 20 meters per second. Suddenly, the driver steps on the gas, and within a few seconds, the speed climbs to 30 meters per second. Something fundamental has happened here. Not just motion, but a change in motion. This is acceleration in action. Unlike speed, which only tells us how fast something moves, or velocity, which adds direction, acceleration measures how quickly velocity changes over time. It's not just about going faster. It also includes slowing down, known as deceleration, and even changing direction. Take a car making a sharp turn at a constant speed. Even though the speed remains steady, the velocity is changing because the direction is shifting. This means the car is accelerating, even if the driver doesn't press the gas pedal. Acceleration isn't just a concept limited to vehicles, it's everywhere. Pedaling a bicycle increases speed, which means acceleration is happening. That jolt you feel in an elevator when it starts moving or stops suddenly, that's acceleration too. Even Earth itself accelerates as it follows its curved orbit around the Sun, constantly changing direction. One of the most familiar and constant sources of acceleration is gravity. Near Earth's surface, all objects in free fall accelerate at 9.8 meters per second squared, regardless of their mass. This explains why a bowling ball and a feather, in a vacuum, fall at the same rate. From tracking moving vehicles to predicting planetary motion, acceleration gives us the ability to describe and anticipate how objects behave in motion. But motion doesn't change on its own. Something must be causing it: a push, a pull, an unseen force shaping the movement. What makes objects start, stop, or change direction? To answer that, we must explore the next fundamental concept: force. Nothing moves, stops, or changes direction on its own. Every falling raindrop, every gust of wind, every shifting tectonic plate, all are driven by force. Without it, the world would be frozen in stillness. No flowing rivers, no drifting clouds, no motion at all. At its core, force is simply an interaction that causes a change in motion. It can make something start moving, stop, or change direction. Push a ball, and it rolls forward. Catch it, and it comes to a stop. The more force applied, the greater the effect. This is why pushing an empty cart is easy, while moving a heavily loaded one takes much more effort. Greater mass requires greater force to achieve the same motion. Forces come in many forms. Contact forces require physical interaction. Try sliding a book across a table. friction resists the motion, slowing it down. Applied forces create movement, like pushing a door to make it swing open. But forces don't always cause movement. Sometimes they cancel each other out. If, 2, people push on a box with equal force from opposite sides, the box stays still. These are balanced forces, equal and opposite, resulting in no movement. But if one person pushes harder, the forces become unbalanced, and the box moves in the direction of the stronger force. From the snap of a stretched rubber band to the impact of a hammer driving a nail, every action in the physical world is governed by force. Whether gentle or immense, force is the reason objects move, interact, and respond to their surroundings. But force alone doesn't tell the whole story. Why do objects resist changes in motion? Why does a car lurch forward when the brakes are suddenly hit? To answer that, we must explore the next fundamental concept: inertia. A bicycle glides effortlessly along the road, balanced and steady. But the moment it slows down and stops, it topples over. A train, once in motion, takes miles to come to a halt. A passenger in a speeding car feels the sudden jolt forward when the brakes are slammed. These everyday experiences are all governed by inertia, the natural resistance of objects to changes in motion. Inertia is not just a force. It is a fundamental characteristic of matter itself. If something is at rest, it prefers to stay that way. If something is moving, it resists any attempt to slow it down or change its direction. The heavier the object, the stronger its inertia. That's why a small push can send a rolling soccer ball across the field, but moving a parked truck requires immense effort. This concept isn't just a curiosity. It is woven into the very fabric of how we design, build, and interact with the world. Engineers take inertia into account when designing safer cars by adding crumple zones that absorb impact forces. Athletes adjust their movements based on inertia, whether it's a sprinter maintaining momentum or a gymnast controlling their landing. Even spacecraft drifting in the vacuum of space must use precise bursts of thrust to counteract inertia, as there is no air resistance to slow them down naturally. But inertia doesn't just shape small-scale movement, it dictates the motion of planets, stars, and galaxies. Earth continues to orbit the Sun not because it is actively propelled, but because inertia keeps it moving while gravity bends its path. The same principle applies to entire galaxies, where celestial bodies travel along predictable trajectories, following the inertia set in motion billions of years ago. By understanding inertia, we gain the ability to predict movement, control forces more effectively, and push the boundaries of technology. But inertia alone doesn't tell the whole story. Why does a train take so long to stop? Why does a bullet strike with such power despite its small size? The answer lies in the next key concept: momentum, the true force behind unstoppable motion. A bullet rips through steel, a football slams into a player's hands with a sting, and a train, even when brakes are applied, keeps rolling for miles before coming to a stop. These moments aren't just about motion. They're about momentum, the true measure of an object's impact in motion. Momentum is the product of mass and velocity. The greater the mass or speed, the more momentum an object carries. That's why a slow-moving truck can pack more force than a speeding bicycle. It's not just about how fast something moves, but how much mass is in motion. Unlike speed, momentum isn't just a number. It's a vector quantity, meaning it has both magnitude, how much, and direction, where it's going. If a car is traveling east at 60 mph, its momentum is also directed east. If the car turns or slows down, its momentum changes. But momentum isn't easily lost. One of the most fundamental principles in physics is the conservation of momentum. In a closed system, momentum doesn't disappear, it simply transfers. This is why, in collisions, the total momentum before impact equals the total momentum after. When two billiard balls collide, momentum transfers smoothly from one to the other with minimal energy loss. This is an elastic collision. In a car crash, however, some of the momentum converts into sound, heat, and deformation, making it an inelastic collision. Momentum even governs movement beyond Earth. In the vacuum of space where no air resistance exists, astronauts rely on conservation of momentum to maneuver. If they push an object in one direction, they move in the opposite direction with equal force. This same principle allows spacecraft to adjust their course using tiny thrusters. Momentum is what allows objects to interact, transfer energy, and keep moving until something stops them. But what happens when motion needs to change in an instant? How can a sudden force alter an object's momentum? To answer that, we must explore the next critical concept: impulse, the power of force over time. A boxer takes a hit, absorbing the shock. A baseball bat connects with a fast pitch, sending the ball flying. A car crashes, but in an instant, the airbags deploy, cushioning the blow. These moments are all ruled by the same principle: impulse, the force that changes an object's momentum. Impulse isn't just about how much force is applied, but how long it is applied. A brief, sharp hit delivers one kind of impact, while a sustained force over time creates another. The longer a force acts on an object, the greater the change in its motion. This is why a light tap on a soccer ball only nudges it forward, but a powerful, well-timed kick launches it across the field. The difference is in the impulse, the amount of force delivered, and the duration of its impact. This concept isn't just about making things move, it's also about controlling force. In critical situations, in a car crash, the sudden stop could be catastrophic, but airbags and crumple zones stretch out the time of impact. By increasing the time over which the collision occurs, they reduce the force experienced by passengers, making injuries far less severe. The same idea applies in sports. When a baseball player catches a fast-moving ball, they instinctively pull their glove back upon impact, extending the time over which the ball slows down. This small movement spreads out the force, preventing injury to the hand. Impulse is everywhere, shaping movement, impact, and safety in ways we often don't notice. It determines how athletes perform, how vehicles protect lives, and how objects interact in high-speed collisions. But impulse is just one part of the bigger picture. What fundamental laws govern all these forces and motions? To find out, we must explore the foundation of classical physics, Newton's laws. Every time you push open a door, ride a bike, or watch a rocket launch into space, you're witnessing the fundamental principles that govern motion. Newton's three laws of motion form the very foundation of classical physics, explaining how objects move and interact with forces. Simple yet profound. These laws shape everything from the flight of an airplane to the way your body reacts in a sudden stop. The first law, often called the law of inertia, states that an object at rest stays at rest, and an object in motion stays in motion unless acted upon by an external force. A book lying on a table won't suddenly move on its own. just as a moving car won't stop instantly when the brakes are applied. This is inertia in action, the natural resistance of objects to changes in motion. It's the reason passengers lurch forward when a car suddenly halts and why astronauts float freely in space, untouched by forces of friction. The second law establishes the relationship between force, mass, and acceleration. The harder you push an object, the faster it moves. However, a heavier object requires more force to achieve the same acceleration. That's why kicking a soccer ball sends it flying, but kicking a bowling ball barely moves it. This law governs everything from how bicycles pick up speed to how rockets escape Earth's gravity. The third law is the famous, for every action, there is an equal and opposite reaction. When you jump off a boat, you push the boat backward while propelling yourself forward. Rockets work the same way. By expelling exhaust gases downward, they generate thrust upward. This principle explains why birds can fly, why fish propel themselves through water, and how jet engines produce power. Together, Newton's three laws create a framework for understanding motion in nearly every situation imaginable. They predict how objects behave, whether it's the orbit of planets or the design of high-speed trains. But forces don't just exist in isolation. Some are so powerful and universal that they shape entire planets, guide celestial bodies, and influence everything in existence. What force holds the universe together? To answer that, we must explore the next great principle: gravity. Without gravity, nothing would be the same. Planets wouldn't stay in orbit, galaxies wouldn't form, and even the air we breathe wouldn't cling to Earth. Right now, gravity is the invisible hand pressing you to the ground, keeping everything in place. It is the silent architect of the universe, holding reality together. At its core, gravity is the attraction between any two objects with mass. The greater the mass, the stronger the pull. This is why Earth's gravity keeps the Moon in orbit, while the Sun's immense gravity commands the motion of the planets. Without this force, the planets would drift aimlessly into space, and the night sky would look vastly different. For centuries, Newton's law of universal gravitation provided an elegant explanation. Every object exerts a force on every other object, and this force weakens with distance. But Newton's theory only told part of the story. Einstein took it further. According to general relativity, gravity isn't just a force, it's the very shape of space and time. Imagine placing a heavy ball on a stretched rubber sheet. The surface curves under its weight, creating a dip. A smaller ball placed nearby will roll toward the dent, just as a planet orbits a star by following the curved space created by its mass. Gravity, then, is not just a pull, it is the bending of reality itself. And gravity's influence doesn't stop with motion, it even affects time. Near incredibly strong gravitational fields, such as black holes, time slows down compared to regions with weaker gravity. This phenomenon, known as gravitational time dilation, has been proven through satellites orbiting Earth. Atomic clocks in space tick slightly faster than those on the planet's surface. From the gentle pull that causes a raindrop to fall to the unfathomable grip of black holes warping time and space, gravity is the force that dictates motion on every scale. But what happens when there's nothing left to resist gravity's pull? What does it feel like to surrender completely to free fall? To answer that, we must explore the next stage of motion: free fall. A skydiver leaps from a plane, an apple detaches from a branch, a meteor plunges toward Earth. Each of these moments is a perfect display of free fall, motion ruled by gravity alone. No resistance, no interference, just an object surrendering, completely to the pull of an unseen force. In the absence of air resistance, all objects, no matter their mass, fall at the same rate. This idea, once debated, was famously demonstrated by Galileo at the Leaning Tower of Pisa, where he dropped two objects of different masses and found they landed at the same time. Centuries later, this experiment was repeated on the Moon, where an astronaut dropped a feather and a hammer in the vacuum of space. Without air to slow one more than the other, they hit the lunar surface simultaneously, proving that gravity acts uniformly on all objects. On Earth, the acceleration due to gravity is 9.8 meters, meaning that with each passing second, a freely falling object gains 9.8 meters per second in speed. This steady increase in velocity continues until another force, like air resistance or the ground, interferes. But free fall isn't just about objects dropping straight down. It extends far beyond Earth, shaping celestial mechanics itself. The Moon is in perpetual free fall around Earth, not crashing into the planet because its curved motion creates an orbit. The same principle applies to satellites, which are constantly falling toward Earth but move forward fast enough that they never actually hit the surface. Even in space, where astronauts appear to float weightlessly, they aren't defying gravity. They are simply falling at the same rate as their surroundings, caught in an endless descent that never reaches an end. This is why spacecraft and space stations orbiting Earth experience microgravity, a continuous state of free fall. Free fall reveals one of the most fundamental truths about gravity. It doesn't discriminate. Whether an object is as light as a feather or as massive as a boulder, if gravity is the only force acting, the rules remain the same. But in the real world, motion is rarely unopposed. There is an invisible force constantly working against. Movement, slowing objects down, wearing surfaces away, and shaping how things move through the air. To understand that, we must explore the next great force: friction. Without friction, life as we know it would be impossible. Walking would be a struggle. Cars wouldn't stop, and even nails wouldn't stay in place. It's a force that both resists motion and enables control, shaping nearly everything we do. Its core, friction arises whenever two surfaces come into contact, resisting their movement relative to each other. Even materials that feel smooth to the touch aren't truly smooth. Under a microscope, they have tiny imperfections, bumps, and ridges. When two surfaces press together, these microscopic irregularities interlock, creating resistance. The rougher the surface, the greater the friction. Friction comes in two main forms. Static friction is what keeps objects at rest. Imagine trying to push a heavy box. It won't move at first because static friction resists your effort. But the moment you push hard enough, the box starts to slide, transitioning into kinetic friction. This type of friction is weaker than static friction, which is why it's harder to start moving an object than to keep it in motion. The amount of friction depends on how strongly two surfaces press together, known as normal force. A heavier object pressing down on a surface experiences more friction because it pushes the surfaces together more tightly. However, friction does not depend on surface area. A wide tire and a narrow tire on the same road experience nearly the same friction because what matters is the force distribution, not the size of the contact area. Friction is both a challenge and a tool. It enables brakes to stop vehicles, athletes, to grip the ground, and even heat to be generated when you rub your hands together. Engineers work to reduce friction in machines using lubricants, making them more efficient. while athletes and drivers find ways to increase friction for better control. But friction doesn't just happen between solid surfaces. When objects move, through air, another kind of friction comes into play, one that shapes how things fall, fly, and move through the sky. To understand that, we must explore the next invisible force: air resistance. Drop a rock and a feather at the same time, and the rock reaches the ground first. Not because it's heavier, but because of air resistance, the invisible force that pushes against objects as they move through the air. Without it, everything would obey the simple rules of free fall, accelerating at the same rate regardless of size or shape. But in reality, air resistance changes how objects move, how fast they fall, and even whether they can glide through the sky. Air resistance, also called drag, occurs because air isn't empty. It's filled with countless molecules. When an object moves, it must push through these molecules, colliding with them and creating resistance. The faster an object moves, the more molecules it hits, and the greater the resistance becomes. This is why cyclists crouch forward to reduce drag, why race cars are designed with sleek aerodynamic shapes, and why parachutes expand to maximize air resistance and slow descent. The effect of air resistance depends on speed, shape, and surface. Area. A streamlined bullet slices through the air with minimal resistance, while a broad parachute catches the wind and slows dramatically. This force is why skydivers plummet quickly at first, but then stabilize at a constant speed, known as terminal velocity. At this point, gravity pulling them down and air resistance pushing up become equal, preventing further acceleration. Without air resistance, all objects would fall at the same rate, as seen in the vacuum of space. But here on Earth, air resistance plays a vital role in everything from aviation to meteorology. Airplanes depend on controlled resistance to generate lift, allowing them to stay aloft, while meteors entering the atmosphere experience such extreme air resistance that they burn up before ever reaching the ground. Weather shaping how objects fall, allowing flight, or even influencing weather patterns, air resistance is one of the most important forces in our world. But motion doesn't just depend on resistance. It also depends on the work done to move objects in the first place. What exactly is work in physics, and how does it shape energy and movement? To answer that, we must explore the next key concept. Work. Lifting, pushing, pulling, these all feel like work, but in physics, work is not about effort, it's about energy being transferred. Every time you move an object by applying force, you're doing work. But if there's no movement, no matter how much effort you exert, no work has been done in a physical sense. Imagine pushing against a solid wall with all your strength. Your muscles burn, sweat drips, and exhaustion sets in. But if the wall doesn't move, no work has actually occurred. Work only happens when force results in displacement, when an object physically moves. Lifting a book from the floor to a shelf, kicking a soccer ball, or pedaling a bicycle. These are all examples of work because they involve force moving an object over a distance. The amount of work done depends on two key factors: the force applied and the distance moved. Lifting a heavy box onto a high shelf requires more work than lifting a lighter one to the same height. Likewise, moving an object a longer distance increases the total work done. Work also depends on direction. If the force is applied in the same direction as the movement, like pulling a cart forward, all the energy goes into the work. But if the force is applied at an angle, such as pushing a box at a slant, only part of the effort contributes to the actual movement. The rest is wasted in other directions. Work is fundamental to understanding how energy flows through systems. It explains how engines generate power, how machines operate, and even how the human body moves. Every time work is done, energy is transferred, allowing systems to function, from industrial machines lifting tons of material to something as simple as tossing a ball across a field. But where does this energy come from? What fuels every motion, every transformation, every force in the universe? To answer that, we must explore the next great principle: energy, the currency of the universe. Every motion, every transformation, every force at play, from the burning heat of the sun to the beating of your heart, is powered by energy. It is the driving force behind everything, making motion possible, fueling life, and shaping the universe itself. At its core, energy is the ability to do work. It exists in many forms, constantly shifting and adapting. Kinetic energy propels moving objects, while potential energy waits in stored form, like a stretched spring or a rock perched at the edge of a cliff. Thermal energy spreads as heat, and chemical energy fuels life itself, stored in food and released to power muscles, movement, and even thought. Yet, for all its transformations, energy is never created or destroyed, only transferred or converted. This is the law of conservation of energy, one of the most fundamental truths in physics. The total energy within a system remains constant, merely shifting from one form to another. Picture a roller coaster at its highest peak. At that moment, it holds maximum potential energy, ready to be unleashed. As it plunges downward, that stored energy transforms into kinetic energy, accelerating the coaster. But not all of it goes into speed. Friction and air resistance convert some of the energy into heat, warming the tracks and the air around it. Yet no energy is lost. It simply changes form. Even the food you eat follows this rule. The chemical energy stored in a meal becomes kinetic energy when you move, thermal energy to maintain body temperature, and electrical energy to send nerve signals through your brain. The same principle governs the universe, from the nuclear reactions that fuel the sun to the electrical currents that light up entire cities. Everything in physics, from motion to forces, ultimately connects back to energy. It dictates how objects move, collide, and evolve, whether it's a falling apple or a star being born. But energy comes in many forms, and one of the most important is kinetic energy, the energy of motion itself. A falling raindrop, a speeding bullet, a planet racing through space, anything that moves carries kinetic energy. It is the force behind every motion, the energy that transforms speed into impact, and the reason why movement has power. The amount of kinetic energy an object has depends on two factors: mass and speed. A heavier object carries more kinetic energy than a lighter one moving at the same speed. But speed plays an even greater role. When an object moves twice as fast, it's kinetic. Energy more than doubles, it increases exponentially. This is why a tiny pebble moving at high speed can still cause damage, while a massive boulder sitting still has no kinetic energy at all. The effects of kinetic energy are everywhere. In a car crash, a slow-moving vehicle might only dent a bumper, but a car traveling at high speed can cause complete destruction. The greater the speed, the greater the energy, and the more impact it can have. This is why kinetic energy is a key factor in sports, engineering, and space travel, whether it's designing race cars for maximum efficiency or ensuring that spacecraft can safely re-enter Earth's atmosphere. But kinetic energy isn't just something we can see. It exists even at the microscopic level. The molecules in a substance are constantly in motion, and their kinetic energy determines temperature. The higher their speed, the hotter the substance becomes. This is why friction produces heat. Rubbing your hands together increases molecular motion, generating warmth. Kinetic energy is everywhere, from the smallest atoms to the largest celestial bodies. But energy isn't always in motion. Sometimes it's stored, waiting to be unleashed. To understand that, we must explore potential, energy, the energy of stored power. Not all energy is in motion. Some of it lies in waiting, stored until the right moment to be released. This is potential energy, the hidden power an object holds due to its position, condition, or structure. It is the energy of anticipation, ready to transform into motion the moment a force sets it free. One of the most familiar forms is gravitational potential energy. A rock perched at the edge of a cliff remains still, yet it holds energy simply because of its height. The higher the rock, the greater its potential energy. The instant it falls, that stored energy transforms into kinetic energy, fueling its rapid descent. Potential energy also exists in elastic materials. A stretched rubber band or a pulled-back slingshot holds energy in its tension. The moment you release it, that stored energy propels an object forward. Springs function the same way. When compressed or stretched, they store energy that is unleashed as they snap back to their original shape. But potential energy isn't just mechanical. It exists at the molecular level too. Chemical potential. Energy is stored within the bonds of substances, waiting to be released. The food you eat, the fuel in a car, even explosives all contain locked-in energy that, when triggered, transforms into motion, heat, or combustion. The gasoline in an engine remains inert until ignited, at which point its chemical energy fuels movement. Potential energy is what allows energy to be stored and used exactly when needed, powering everything from hydroelectric dams to muscle movement. It explains how forces build up, how energy is transferred, and how motion is controlled. But energy doesn't just exist. It can be used at different rates. Some systems release energy slowly, while others unleash it in an instant. How quickly work is done and energy is transferred determines power. To understand that, we must explore the concept of power. Two people climb the same flight of stairs. One moves at a steady pace, taking their time, while the other dashes up in seconds. Both have done the same amount of work. They've lifted their body weight to the same height. But the second person has exerted more power because they completed the task in less time. Power isn't just about effort. It's about how quickly energy is transferred or converted. It determines how efficiently something gets from one state to another, whether it's a sprinter launching off the starting blocks, an engine driving a car, or a turbine generating electricity. This concept is everywhere. A high-powered car accelerates faster because it delivers energy more rapidly to its wheels. A brighter light bulb emits more light because it converts electrical energy into visible energy at a faster rate. Even in nature, a roaring waterfall generates immense power as water crashes down, transferring energy to the rocks below in a fraction of a second. Power is also key to efficiency. A powerful machine completes tasks quickly with less wasted energy, while a weaker one might struggle and take longer. This is why power ratings matter. From the wattage of a light bulb to the horsepower of an engine, they indicate how effectively energy is being used. At its core, power is about control over energy. It's not just about raw strength, but about how efficiently and quickly energy flows. From the smallest electrical circuits to massive industrial systems, power fuels the modern world, shaping technology, transportation, and innovation. But no matter how fast energy is transferred, it never disappears. It only changes form. To understand this, we must explore one of the most fundamental laws in physics, the conservation of energy. Energy is never lost. It never disappears. No matter what happens, the total amount of energy in a closed system remains constant. It can change form, moving between states, but it can never be created or destroyed. This is the principle of conservation of energy, one of the most fundamental laws in physics. Imagine a roller coaster at its highest peak. In that moment, it holds a potential energy, stored because of its height. As it begins to descend, that energy transforms into kinetic energy, fueling its acceleration. The faster it moves, the more kinetic energy it has, but the total energy remains the same. Even when friction and air resistance slow the coaster down, that energy isn't lost. It simply transforms into heat, warming the tracks and surrounding air. This principle applies everywhere. A swinging pendulum continuously converts potential energy to kinetic energy and back again, until air resistance gradually converts some of that energy into heat. A car's fuel holds chemical energy, which transforms into motion, sound, and heat when the engine runs. Even our own bodies follow this rule. The food we eat contains stored chemical energy, which powers movement, generates warmth, and fuels essential biological functions. The conservation of energy governs everything, from the smallest atomic reactions to the largest cosmic events. Stars burn by converting nuclear energy into light and heat, illuminating the universe. Even the expansion of the cosmos itself follows energy conservation principles, ensuring that energy is never created or lost, only redistributed across space and time. This law sets a fundamental boundary on what's possible. No machine can ever produce more energy than it consumes. No natural process occurs without an energy transformation. Everything we see, everything we do, is part of an endless cycle of energy shifting from one form to another. But energy isn't the only thing that follows this rule. Motion itself obeys a similar principle. Momentum never vanishes, it only shifts. To understand that, we must explore the next great law of physics, conservation of momentum. Momentum isn't just something objects possess. It's something that must be conserved. In a closed system, unless acted upon by an external force, the total momentum remains constant. This fundamental principle governs everything from the collisions of billiard balls to the motion of planets. Momentum is the product of mass and velocity. The greater an object's mass or speed, the more momentum it carries. But what makes this principle so powerful is that momentum never simply disappears. When objects interact, they exchange momentum, but the total amount remains unchanged. Consider two ice skaters pushing off each other. Each skater moves in the opposite direction, gaining momentum, but their combined momentum before and after the push remains the same. One skater's movement is perfectly balanced by the movement of the other. This same principle applies at every scale, from small interactions to the vastness of space. In the vacuum of space, where there is no friction, momentum conservation is even more pronounced. If an astronaut throws an object forward, they move. Backward in response, propelled by the very law that governs motion. Rockets operate on the same principle. By expelling fuel at high speed, they push themselves forward, demonstrating conservation of momentum in action. Even in violent, high-speed collisions, momentum is never lost, only redistributed. In a car crash, the momentum of the vehicles transfers upon impact with energy dissipating into sound, heat, and deformation. The system remains in perfect balance even when the results appear chaotic. Momentum conservation isn't just a principle. Of Newtonian physics, it extends into quantum mechanics, where even subatomic particles obey this unbreakable rule. Every movement, every impact, every shift in motion adheres to this law, ensuring that no matter how unpredictable a system seems, its total momentum remains the same. But momentum isn't the only thing that ties motion and energy together. There's a deeper connection between the work done on an object and the energy it gains or loses. To understand this, we must explore the next key concept, the work-energy theorem. Energy doesn't just appear, it must be transferred. This is the foundation of the work-energy theorem, which states that the work done on an object directly translates into a change in its energy. Whether it's speeding up a car, lifting a heavy weight, or stopping a moving object. Work and energy are two sides of the same equation. Imagine pushing a heavy box across the floor. The harder you push, the faster it moves. That effort, the force you apply over a distance, is work, and the result is the box gaining kinetic energy. The more work you do, the more energy the box gains, increasing its speed. Now consider a moving car that suddenly slams on the brakes. The friction between the tires and the road does negative work, reducing the car's kinetic energy until it comes to a complete stop. Work doesn't just add energy, it can take it away too. But this relationship goes beyond just moving objects. When you lift something against gravity, you do work against the force pulling it down. That work is stored as potential energy, ready to be released. Drop the object and that stored energy converts back into motion. Every action, every force applied over a distance results in an energy transfer. The work-energy theorem ties together force, motion, and energy into a single principle. Whenever a force acts over a distance, it transfers energy. This rule explains how engines generate power, how athletes build momentum, and how machines function efficiently. No work, no energy change. That's why the work-energy theorem is a cornerstone of physics. It proves that energy isn't just a property. It's something that must be transferred through action. Every movement, every shift in speed, every force applied reshapes energy, fueling the mechanics of the universe. But energy and motion aren't always evenly distributed. In any system, there's a point where mass is perfectly balanced. A point that determines how objects rotate, move, and stay stable. To understand this, we must explore the concept of center of mass. Balance a pencil on your finger, and you'll notice that only one point keeps it stable. That point is its center of mass, the average position of all the mass in the object. It's the point where an object behaves as if all its mass were concentrated, making it essential for understanding motion, stability, and equilibrium. Every object, whether simple or complex, has a center of mass. A ruler, a spinning wrench, a rocket, even the human body. Each follows predictable rules of motion based on this invisible balance point. If you toss a wrench into the air, its individual parts may rotate unpredictably, but its center of mass follows a smooth, predictable path. This principle is why athletes, dancers, and engineers all rely on an understanding of center of mass. A gymnast twisting midair instinctively adjusts their body to control their center of mass. A rocket must maintain a precise balance of mass to stay stable as it soars through the atmosphere. Even a speeding car depends on this concept. If the center of mass shifts too much during a turn, the vehicle could roll over. Surprisingly, the center of mass doesn't have to be inside the object itself. A hollow ring, for example, has its center of mass at its geometric center, where there's no physical material. In humans, the center of mass constantly shifts with posture and movement. When standing upright, it's near the belly, but lean forward, and it shifts forward too. This concept is not just theoretical, it's a cornerstone of physics and engineering. Buildings are designed with a low center of mass to resist tipping over. Spacecraft require precise mass distribution to ensure controlled motion in zero gravity. Robots and machines use center of mass calculations to maintain balance and efficiency. Understanding the center of mass helps explain why objects topple, how forces act on a system, and what keeps movement stable or chaotic. It is the invisible anchor of motion, defining how things balance, rotate, and move through space. But mass alone doesn't determine stability. There's another key factor that controls how objects interact with gravity. To understand that, we must explore the next crucial concept: the center of gravity. Try balancing a pencil on your finger. There's only one spot where it won't tip over. That point is its center of gravity, the location where an object's weight is perfectly balanced in all directions. Whether it's a spinning gymnast, a towering skyscraper, or a speeding race car, the center of gravity determines stability, movement, and control. The center of gravity, CG, is the average location of an object's weight distribution. For symmetrical objects like spheres or cubes, the CG is at the geometric center. But for irregularly shaped objects, the CG shifts depending on mass distribution. A hammer, for example, has its center of gravity closer to the heavy metal head than the lighter handle, making one end feel heavier than the other. In everyday life, stability depends on where the CG is positioned. A lower center of gravity makes objects harder to tip over, which is why race cars are designed to hug the ground and why pyramids have wide bases, allowing them to stand for centuries. But when the CG moves beyond an object's base of support, it topples. This is why tightrope walkers use long poles to lower their CG, increasing balance and reducing the risk of falling. Humans constantly adjust their center of gravity with every movement. When standing upright, the CG is near the waist, but lean forward too much and it shifts outward, increasing the risk of falling. Athletes and performers train to manipulate their CG for maximum control. Sprinters lean forward at the start of a race to shift their CG ahead, while ballet dancers adjust their limbs midair to maintain balance during jumps. From engineers designing stable bridges to backpack manufacturers making loads feel lighter, understanding the center of gravity is essential for stability, safety, and performance. But stability isn't just about balance. It also plays a crucial role in how objects rotate, spin, and move in circular motion. To understand that, we need to explore the next key principle: rotational motion. A bicycle wheel turns, a figure skater twirls, and the Earth itself rotates on its axis. Unlike objects that move in a straight line, Some objects move by spinning around a fixed point. This is rotational motion, the physics of objects that turn, rotate, and roll. Rotational motion follows many of the same principles as linear motion, but with a twist, literally. Instead of position, we use angular displacement to describe how far something has rotated. Instead of velocity, we use angular velocity to measure how fast it's spinning. And instead of force, we use torque, which determines how effectively a force can cause an object to rotate. Torque is something you experience every day. Imagine trying to open a heavy door. Pushing near the hinge requires a lot of effort, but pushing at the edge makes it much easier. That's because the force applied farther from the pivot point creates more torque, making rotation more effective. Another key concept in rotational motion is moment of inertia, which is like rotational mass. It determines how resistant an object is to changes in its spin. A spinning figure skater demonstrates this principle perfectly. When they pull their arms in, they spin faster. When they extend their arms, they slow down. That's because bringing mass closer to the axis of rotation reduces the moment of inertia, making spinning easier. Rotational motion isn't just found in small objects, it shapes the universe itself. The Earth spins on its axis, creating day and night. Planets orbit stars, governed by the interplay of rotation and gravity. Machines, from car engines to wind turbines, rely on rotational motion to generate power. Understanding rotational motion unlocks the mechanics behind countless natural and engineered systems, revealing how spinning objects behave in ways that are both predictable and profound. But not all objects spin the same way. Some resist changes in their rotation more than others. To understand why, we need to explore the next key concept, moment of inertia. Trying to spin a door by pushing near the hinges versus pushing at the edge feels completely different. The effort required changes based on where the force is applied, and this difference is due to moment of inertia, the rotational counterpart of mass in linear motion. It determines how much resistance an object has to changes in its rotation. Just like mass affects how hard it is to push an object in a straight line, moment of inertia affects how hard it is to make an object spin. But it's not just about how much mass an object has, it's about how that mass is distributed relative to the axis of rotation. The farther the mass is from the axis, the greater the moment of inertia, making it harder to spin. This is why a figure skater can spin faster by pulling their arms in. Reducing the distribution of mass decreases the moment of inertia, allowing rotation to speed up. Different shapes have different moments of inertia. A solid sphere rotates more easily than a hollow one of the same mass and radius because more of its mass is concentrated near the center. A long rod spun about its center rotates more easily than the same rod spun from one end because the distribution of mass relative to the rotation point affects resistance. Moment of inertia isn't just a concept. It's crucial in engineering, physics, and sports. In vehicles, flywheels store rotational energy by maximizing inertia, stabilizing motion. In athletics, gymnasts and divers adjust their body positions to control their spin. Even celestial bodies like planets and stars follow these principles, shaping their rotational dynamics. Moment of inertia explains why some objects rotate easily while others resist rotation. It governs everything from simple mechanical systems to the spinning motion of entire galaxies. By controlling the distribution of mass, we manipulate rotational motion, applying the same fundamental physics whether we're spinning a wheel, designing a machine, or launching a spacecraft. But mass distribution isn't the only factor that influences rotation. Where force is applied and how it acts on an object determines how effectively rotation happens. To understand this, we need to explore torque, the force that makes things spin. Push on a door near the hinges, and it barely moves. Push at the edge, and it swings open effortlessly. This is torque, the rotational equivalent of force. It determines how effectively a force causes an object to rotate around an axis. Torque isn't just about how much force is applied, it also depends on where and how the force is applied. The farther from the axis you push, the greater the torque. That's why wrenches have long handles. By increasing the distance from the pivot point, you generate more torque with the same effort. If you apply force at an angle, only the perpendicular component of that force contributes to rotation. This is why doors, levers, and pedals work best when force is applied at just the right point. A seesaw is a perfect example of torque in action. If two people of equal weight sit at equal distances from the center, balance is maintained. But if one moves closer to the center, their torque decreases, causing the other side to tip. The same principle explains why gears turn, why planets rotate, and why bridges remain stable under stress. Torque is crucial in both nature and engineering. It powers the rotation of the Earth, the motion of gears, and the effectiveness of mechanical systems. Engineers rely on precise torque calculations to design car engines, wind turbines, and complex machinery, ensuring that rotational forces are controlled and used efficiently. Understanding torque is key to mastering rotational motion. Whether opening a door, tightening a bolt, or designing advanced machinery, torque is the invisible force that dictates how things turn, pivot, and move. It bridges everyday experiences with the deeper mechanics of physics, making the motion of the world not just predictable, but controllable. But torque is just one part of rotational motion. Once an object starts spinning, what keeps it going? How do rotating bodies maintain their speed and stability? To answer that, we need to explore the next key concept: angular momentum. A figure skater spins effortlessly on the ice, arms extended. The moment they pull their arms in, they rotate faster, without any additional push. This is angular momentum in action, a fundamental principle that governs all rotating objects, from spinning tops to entire planets orbiting the Sun. Angular momentum is the rotational equivalent of linear momentum. In linear motion, an object continues moving unless acted upon by an external force. Similarly, in rotational motion, an object keeps spinning unless an external torque acts on it. Once something starts rotating, it naturally resists changes in its spin, just as a moving car resists stopping. The key factors that determine angular momentum are an object's mass, its rotational speed, and how that mass is distributed relative to the axis of rotation. The most striking feature of angular momentum is its conservation. Unless an external torque interferes, angular momentum remains constant. This explains why a spinning skater speeds up when they pull their arms in, by reducing the distribution of mass around the axis. The rotation rate increases to compensate. The same principle applies to planets moving in their orbits. When they drift closer to the Sun, they speed up, and when they move farther away, they slow down. Angular momentum is not just a curiosity, It plays a crucial role in engineering, space exploration, and even daily life. Gyroscopes, which rely on angular momentum, help stabilize ships, airplanes, and even smartphones, keeping them aligned. In space, astronauts use angular momentum to maneuver spacecraft without the need for external forces. Even entire galaxies rotate based on the conservation of angular momentum, shaping the very structure of the universe. Understanding angular momentum reveals why rotating objects behave the way they do, from a child's spinning toy to the motion of celestial bodies. Once set in motion, rotation follows precise and unchanging laws, shaping the universe at every scale. But angular momentum isn't just a force, it's a conserved quantity, meaning it never disappears, only transfers. How does this conservation principle shape motion in physics and beyond? To answer that, we must explore the conservation of angular momentum. A figure skater glides across the ice, arms stretched wide. With no external force, they pull their arms inward, and instantly they begin to spin faster. This change in speed without any push is a perfect demonstration of the conservation of angular momentum, one of the most fundamental laws in rotational physics. Angular momentum, like linear momentum, is a quantity that describes motion, but specifically motion in a circular path. And just like energy and linear momentum, angular momentum is conserved. If no external torque acts on a system, its total angular momentum remains constant. So, what changes when the skater pulls in their arms? Their moment of inertia, their resistance to rotational change, decreases. To keep angular momentum conserved, something else must adjust. In this case, the skater's rotational speed increases, spinning faster to compensate for the shift. In mass distribution, this exchange between inertia and speed happens automatically, perfectly balanced by the laws of physics. But this principle extends far beyond the ice. In space, where there's virtually no friction or resistance, conservation of angular momentum governs the rotation of planets, stars, and galaxies. When a star collapses into a smaller, denser object, like a neutron star, its moment of inertia drops drastically. To conserve angular momentum, the star spins faster and faster, sometimes rotating hundreds of times per second. Even in our everyday lives, the principle appears in subtle ways. Sit in a spinning office chair, tuck in your arms, and feel yourself. Accelerate, or observe how a fidget spinner keeps rotating, maintaining its angular momentum until an external force, like friction, slows it down. Engineers use this principle to control spacecraft orientation without using fuel, simply by shifting mass within the vehicle. It's an elegant solution in environments where external forces are minimal, but precision is essential. Whether in sports, engineering, or the cosmos, the conservation of angular momentum reveals a deeper truth. Once rotation begins, it persists, unless something intervenes. It's this unwavering balance that governs the motion of everything from tiny toys to spinning stars. But not all spinning motion is free. Some objects require a force that constantly redirects them to maintain circular paths. To understand this special kind of force, we now turn to centripetal force. Swing a ball on a string in a circle and you might expect it to fly outward, but it doesn't. Instead, it stays locked in its circular path. The reason lies not in an outward push, but in a constant inward pull, known as centripetal force. A force essential to any object moving in a circle. Centripetal force doesn't act in the direction the object is traveling. Instead, it pulls perpendicular to its motion, always toward the center of the circle. Without this force, an object would obey inertia and fly off in a straight line. It's not that something is pushing it outward, it's that, without the inward force, there's nothing to hold it in. Think of a car taking a sharp curve. It stays on the road because friction between the tires and pavement provides the necessary centripetal force. If the road is icy and friction is reduced, the car can no longer hold the curve and slides outward. The same principle governs celestial mechanics. Gravity acts as the centripetal force that keeps Earth in orbit around the Sun, constantly redirecting its motion inward so it doesn't drift off into space. The Moon orbits Earth for the very same reason. Gravity is the ever-present inward pull. The strength of this force depends on an object's mass, speed, and the radius of the circular path. A heavier object or one moving faster requires a stronger centripetal force to stay on its curve. Similarly, decreasing the radius, like a skater pulling their arms inward while spinning, increases the required force to maintain the same circular motion. Centripetal force is everywhere, quietly working, behind the scenes. It keeps satellites in orbit, roller coasters on their tracks, and entire galaxies in motion. Whether in engineering, sports, or astrophysics, mastering centripetal force is key to controlling curved motion, ensuring stability, safety, and precision. But, while forces like this help us maintain motion, they're not always raw power. Sometimes motion is achieved not by increasing effort, but by making tasks easier through clever design. To understand that, we enter the world of simple machines. Opening a door, cutting paper, or raising a flag might seem like ordinary actions, but behind each is a powerful principle of physics: simple machines. These basic mechanical devices are designed to make work easier by either amplifying force or changing its direction. Though simple in structure, they are the foundation of nearly all mechanical systems: past, present, and future. There are 6 classic types of simple machines, each uniquely effective. The lever uses a rigid bar that pivots around a point called a fulcrum. Whether it's a seesaw, a crowbar, or a bottle opener, applying force on one side allows you to lift or move an object on the other with greater ease. The pulley changes the direction of force using a rope and wheel, making it possible to lift heavy loads vertically with less effort, as seen in cranes or flagpoles. The wheel and axle is another powerful tool. It reduces friction and allows smooth, controlled motion found everywhere from doorknobs to bicycles. The inclined plane, or ramp, lets you raise objects by spreading the effort over a longer distance. It's easier to push a heavy cart up a slope than to lift it straight up. The wedge converts force into a splitting action, cutting or separating materials like wood or fabric with tools such as axes or knives. Lastly, the screw is essentially an inclined plane wrapped around a cylinder, converting rotational force into linear movement, securing or lifting with precision. These machines don't create energy, they restructure it. A longer ramp requires less force but covers more distance. A lever with the fulcrum placed just right can magnify a small input into a large output, moving objects that would otherwise be too heavy. Engineers combine these simple machines to build complex systems. Gears, engines, cranes, and countless other tools all trace their function back to these 6 elemental forms. From the technology of ancient civilizations to the innovations of modern industry, simple machines have shaped how we work, move, and build. But understanding how a simple machine multiplies force leads us to a deeper question. Just how much? Does it multiply it by? To answer that, we need to explore the next concept: mechanical advantage. Try lifting a massive boulder with your bare hands. It's nearly impossible. But place a well-positioned lever beneath it, and suddenly, the impossible becomes manageable. This is the power of mechanical advantage, a principle that allows simple machines to amplify force, making hard work easier by redistributing effort. Mechanical advantage is essentially a measure of how much a machine multiplies your input. It compares the force you put into the system to the force the system gives back in return. A crowbar, for instance, lets you apply a small amount of effort over a greater distance, and in doing so, it delivers a much larger output force. Lifting, or prying something that would be far too heavy to move on its own. Different simple machines create mechanical advantage in different ways. A lever can either multiply force or increase speed depending on where the fulcrum is placed. A pulley system reduces the effort needed to lift an object by spreading the load across multiple ropes, easing the burden. An inclined plane lets you push heavy objects upward with less force by extending the distance over which the force is applied. In every case, the total work remains the same, but the force required at any moment is reduced. A key concept here is trade-off. Machines may lower the force you need to apply, but they increase the distance you have to work over. A longer ramp takes less effort to ascend, but you'll have to walk farther. A pulley may have the required force, but you'll have to pull twice as much rope. Mechanical advantage is a cornerstone of engineering and design, enabling us to build cranes, gears, bicycles, and bridges, tools and systems that expand our physical limits. By understanding how to manipulate force through clever setups, engineers create machines that help us lift, cut, and move with minimal effort and maximum efficiency. But not all motion is about lifting or pushing. Some systems move back and forth, repeating in cycles that shape both nature and technology. To understand this rhythmic side of physics, we turn to the study of oscillations, a plucked guitar string, a swinging pendulum, the gentle ticking of a clock. These are all examples of oscillations, one of the most foundational and elegant forms of motion in physics. An oscillation is any repetitive back-and-forth movement around a central resting point known as the equilibrium position. This motion begins when an object is displaced from its equilibrium. As soon as it's moved, a restoring force acts to pull it back. But it doesn't stop there. Instead of returning and settling, the object overshoots, moving past the center in the opposite direction. This sets off a continuous rhythmic cycle of motion. A perfect example is a mass on a spring. Pull it down and release it, and the mass bounces up and down. The farther it is pulled, the stronger the spring pulls it back. This push and pull between displacement and restoring force drives oscillatory motion. Oscillations come in many forms. Mechanical oscillations include things like pendulums, tuning forks, and vibrating strings. Electromagnetic oscillations, such as those in alternating electrical currents, involve energy cycling between electric and magnetic fields. Even at the quantum level, particles exhibit oscillatory behaviors, shaping interactions at the smallest scales of matter. Two key properties define oscillations: period and frequency. The period is the time it takes to complete one full cycle, while frequency measures how many cycles occur each second. These values depend on factors like mass, stiffness, or length in mechanical systems, all of which influence how quickly and smoothly an object can oscillate. Oscillatory motion is everywhere, from the beating of a heart to the pulses of light and sound. It powers timekeeping devices, guides electrical signals, and underpins countless aspects of engineering and communication. By understanding oscillations, we gain insight into nature's repeating patterns, learning how to harness them for everything, from measuring time to transmitting sound and data. But oscillations don't just happen in place, they can also travel through space, creating waves that move energy across distances. To explore that, we move next into the world of waves. A pendulum swinging steadily, a mass bouncing up and down on a spring. These are classic examples of simple harmonic motion, SHM, one of the most elegant and predictable types of movement in physics. It's the motion that forms the heartbeat of waves, sound, light, and countless engineered systems. At its core, simple harmonic motion occurs when an object is repeatedly pulled back toward a central equilibrium point by restoring force that is directly proportional to its displacement. In simpler terms, the farther the object is from its rest position, the stronger the force pulling it back. This results in a smooth, rhythmic back-and-forth movement. Take a pendulum. When you displace it from its resting position, gravity pulls it back, but it doesn't stop at center. It swings past, slows, and reverses again, repeating in a consistent cycle. The same happens with a mass on a spring. The further it stretches, or compresses, the more force the spring applies to return it to center. This predictable pattern creates motion that's sinusoidal in nature, smooth, regular, and easy to model mathematically. SHM is defined by two key properties: period, the time it takes to complete one full cycle, and amplitude, the maximum distance, from the equilibrium point. The frequency of the motion, or how many cycles occur per second, is also central to understanding its behavior. These properties depend on factors like mass and stiffness in springs, or length and gravity in pendulums. What makes simple harmonic motion so powerful is its universality. It's not just seen in mechanical systems, but in the oscillations of atoms, electrical circuits, and even quantum systems. It's what allows musical instruments to produce sound, what governs the timing of clocks, and what underlies the vibrations of molecules. By mastering SHM, we gain a deeper understanding of how nature maintains rhythm and balance. It's a bridge between motion and waves, because when SHM travels through a medium, it becomes a wave. And that's where we go next, from individual motion to motion that spreads across space in waves. Drop a pebble into a still pond and watch as ripples spread outward. Though the water itself doesn't flow outward with the waves, the energy does. This is the essence of a wave. A disturbance that transfers energy through a medium or space. Without permanently moving the material it passes through. Waves are one of the most fundamental ways energy moves through the universe. Instead of carrying matter along, waves cause particles to oscillate, to move back and forth or up and down, passing energy through the system. These oscillations can occur in different directions, leading to two main types of waves: longitudinal and transverse. In longitudinal waves, the disturbance moves in the same direction as the wave, like sound traveling through air. In transverse waves, the disturbance moves perpendicular to the direction of the wave, like water ripples or light waves. Some waves, like mechanical waves, require a medium, air, water, or solid ground, to travel. Others, like electromagnetic waves, don't need a medium at all. They can move freely through the vacuum of space, carrying everything from sunlight to radio signals. Waves are defined by key properties: wavelength, the distance between two peaks; frequency, how many cycles occur per second; and amplitude, which reflects the energy carried by the wave. High-amplitude waves carry more energy, while high-frequency waves oscillate more rapidly. From the smallest atomic vibrations to massive ocean swells, waves govern how energy moves through the world. They are the foundation of sound, vision, communication, and even quantum mechanics. Everything from music and speech to X-rays and internet data relies on the wave concept to function. By understanding how waves operate, we unlock the ability to manipulate energy with precision, build advanced technologies, and interpret the deep rhythms of the universe. And to truly grasp wave behavior, we need to dive deeper into one of its defining characteristics: frequency. A hummingbird's wings blur as they flap. A high-pitched whistle slices through the air, and a deep drumbeat rumbles beneath your feet. These moments may feel completely different, but they all share a hidden rhythm: frequency. In physics, frequency is the number of cycles a repeating event completes in 1 second. It tells us how fast something vibrates or oscillates, whether it's a pendulum swinging, a sound wave traveling, or a photon of light racing through space. Frequency is measured in hertz, where 1 hertz equals 1 cycle per second. Imagine a pendulum. If it swings back and forth once every second, it has a frequency of 1 hertz. If it swings 5 times per second, the frequency increases to 5 hertz. The faster the repetition, the higher the frequency. This principle applies to waves across all forms: sound, light, water, and beyond. In sound, frequency determines pitch. Low-frequency waves produce deep, booming bass tones, while high-frequency waves create sharp, high-pitched notes. In light, frequency defines color. Lower frequencies appear as reds and oranges, while higher frequencies shift toward blue and violet hues. But frequency goes far beyond what we can see or hear. It plays a crucial role in radio communication, allowing us to tune into specific channels. It's essential in medical imaging like ultrasounds. Even in biology, heartbeats and brain waves operate at characteristic frequencies that reflect our internal rhythms. At every level, from quantum vibrations to astronomical cycles, frequency governs the tempo of the universe. By understanding it, we gain the power to control waves, shape technologies, and better comprehend the energy patterns that structure our world. To further understand the nature of these repeating motions, we must look at another foundational property of waves: the period, the time it takes for a single cycle to complete. Waves crashing against the shore, a pendulum ticking steadily back and forth, the slow rotation of a Ferris wheel, all of these follow a repeating pattern, and the time it takes to complete one full cycle is known as the period. In physics, the period is the duration of one complete cycle of any repeating event. It could be the time it takes for a guitar string to vibrate, a planet to orbit a star, or a pendulum to swing back to its starting point. The period tells us how long it takes to return to the beginning, and it's typically measured in seconds per cycle. Imagine a Ferris wheel. If it takes 30 seconds for one full rotation, its period is 30 seconds. If it spins faster and completes a full rotation in 15 seconds, the period shortens. The concept remains the same across mechanical systems, waves, and even astronomical cycles. Period is closely related to frequency, the number of cycles in 1 second. The two are inversely proportional. If a wave has a high frequency, it has a short period. If it has a low frequency, the period is longer. One determines how often something happens, the other determines how long each instance lasts. Understanding. Period allows us to make sense of rhythmic motion in everyday life, from the pulse of a heartbeat to the timing of traffic lights. In music, it defines the tempo of a beat. In astronomy, it helps us predict planetary orbits. In wave mechanics, it's vital to understanding how energy travels and repeats. Whether you're measuring the oscillation of a pendulum or the arrival of ocean waves, the period provides a clear way to quantify and predict the natural timing of events. And to further decode the structure of waves, we turn next to another key characteristic: wavelength, the spatial length of each repeating cycle. Stand by the edge of a calm lake and toss in a pebble. Ripples spread out in smooth, repeating circles, and the distance between each peak of those ripples is called the wavelength. It's a fundamental property of waves, shaping everything, from color and sound to how energy travels through space. In physics, wavelength is the physical distance between two identical points in a wave cycle, like crest to crest in an ocean wave, peak to peak in a sound wave, or one complete oscillation in a light wave. While it may seem like a simple measurement, wavelength plays a powerful role in how waves behave and interact with the world. For light waves, wavelength determines color. Longer wavelengths shift toward the red end of the spectrum. Shorter wavelengths lean blue. That's why sunsets glow orange and red. The longer light waves scatter less and travel farther through the atmosphere. In the realm of technology, radio waves with wavelengths as long as skyscrapers can carry signals invisibly across cities and continents, while X-rays, with wavelengths shorter than an atom, can pass through skin and reveal the structure of bones. In sound waves, wavelength helps define pitch. Long wavelengths produce low, rumbling bass tones. Short wavelengths create sharp, high-pitched sounds like whistles. And the way waves interact with their environment also depends on wavelength. Longer wavelengths can bend around obstacles, which is why you can hear someone around a corner, while shorter wavelengths, like those in visible light, travel in straight lines and cast well-defined shadows. From communications and medical imaging to music and astronomy, understanding wavelength is key. It's one of the hidden dimensions through which we perceive and influence the world. Whether shaping the tone of a song, the color of the sky, or the reach of a radio signal, wavelength is one of the universe's most precise and powerful tools. An invisible ruler shaping the patterns of reality. But there's more to a wave than its length. Another key feature is how intense or powerful a wave is. For that, we look next at amplitude, the deep boom of a drum, the brightness of a shining star, the strength of a rumbling earthquake. All of these are shaped by amplitude, the measure of a wave's intensity. Whether you're talking about sound, light, or motion, amplitude is what tells us how powerful a wave really is. In physics, amplitude refers to the maximum displacement from a wave's resting position, how far something moves from its equilibrium during a vibration. Think of a child on a swing. If they barely move, the amplitude is small. But if they soar high through the air, the amplitude is large. The bigger the swing, the greater the energy the system holds. For sound waves, amplitude controls volume. A whisper creates small vibrations, resulting in a low amplitude and a quiet sound. A thunderclap, by contrast, sends large pressure waves through the air. Its amplitude is high, and so is its volume. In light waves, amplitude determines brightness. Dim candlelight has a lower amplitude than the piercing beam of a flashlight. In the world of seismic waves, amplitude determines how strongly the Earth shakes. A small tremor might be barely noticeable, while high-amplitude waves can topple buildings and reshape landscapes. The same principle applies to radio signals, where greater amplitude boosts signal strength, leading to clearer transmissions. Unlike frequency, which defines pitch or color, amplitude defines intensity. Two waves can vibrate at the same rate, but still carry vastly different amounts of energy if their amplitudes differ. It's this quality that determines whether a wave makes a subtle ripple or a dramatic impact. From gentle ripples in a pond to the fury of a supernova's blast, amplitude measures the energy that drives waves forward. It's not just about how waves move, but how much they move and how much they can do. But once you understand how waves move and how strong they are, there's still another question. How fast do they travel? To explore that, we dive next into the concept of wave speed. Stand on the shore and watch the ocean. Some waves roll in slowly, while others race across the water in rapid succession. What makes them different? It's their wave speed, the rate at which energy moves through a medium in the form of a wave. In physics, wave speed is defined as the speed at which a wave propagates through space or a material. It's influenced by two main factors: the wavelength, the distance between wave crests, and the frequency, how many of those crests pass a point per second. Multiply them together, and you get the wave's speed. But wave speed doesn't just depend on the wave itself. It's also determined by the medium it moves through. For example, sound travels at about 343 meters per second in air, but in water it moves nearly 4 times faster. In steel, sound waves can reach speeds of over 5,000 meters per second, thanks to the tightly packed molecules in solids, which transfer vibrations more efficiently. Light waves have their own unique behavior. In a vacuum, light travels at the fastest speed possible in the universe, about 300,000 kilometers per second. But when light enters materials like glass or water, it slows down and bends, a phenomenon known as refraction, caused by interactions with atoms in the medium. Even ocean waves have their quirks. Their speed is influenced by gravity and water depth. In deep water, waves with longer wavelengths move faster, creating those smooth rolling swells that stretch across the open sea. As they reach the shallows, they slow down, grow taller, and eventually crash onto shore. Understanding wave speed is crucial across science and technology. It helps seismologists detect earthquakes, telecommunications engineers transmit data through fiber optic cables, and astronomers analyze light from distant stars and galaxies. Whether moving through air, water, earth, or space, wave speed determines how quickly energy and information travel, shaping our understanding of everything from sound and light to the very fabric of the universe. And speaking of sound, let's take a closer look at one of the most familiar and fascinating types of waves: sound waves. From the rumble of thunder in the distance to the creak of a floorboard beneath your feet, every sound you hear is carried by sound waves, invisible vibrations moving through matter. Whether traveling through air, water, or solid objects, these waves are how energy is transmitted from one point to another, bringing the world of sound to life. At the heart of every sound is vibration. When an object moves, like a guitar string being plucked or a speaker cone pulsing, it disturbs the particles around it, typically molecules in the air. These particles get pushed together in some places, compression, and spread apart in others, rarefaction, creating a pattern of alternating high and low pressure. That pattern propagates outward, forming a longitudinal wave that moves energy through the medium. Unlike light, sound cannot travel through a vacuum. It needs a medium, something, with particles to vibrate. That's why space is silent. Without air or other material, there's nothing to carry the wave. But in denser materials, sound moves faster. In water, sound travels about 4 times faster than in air, and in steel, it can reach speeds over 5,000 meters per second, because the molecules are more tightly packed, enabling faster energy transfer. Sound. Waves also differ in frequency. How many vibrations happen per second? High-frequency sound waves produce high-pitched tones like a whistle, while low-frequency waves create deep, booming sounds like a bass drum. This full range of vibrations, from bass to treble, shapes the way we experience music, speech, and the world around us. Beyond human hearing, sound waves power technologies like ultrasound imaging, sonar navigation, and even earthquake detection. They let us communicate across distances, sense danger, and explore environments where light cannot reach. In every whisper, every note, every distant roar, sound waves are at work, translating vibration into sensation, turning motion into meaning, and filling the physical world with the language of energy. But sometimes, a sound doesn't just pass through, it grows stronger and more intense with each repetition. That phenomenon is called resonance, and it's where we're headed next. Give a swing a gentle push at just the right moment, and it soars higher with barely any effort. This simple act is a perfect illustration of resonance, a powerful and widespread phenomenon where an object or system vibrates with increasing intensity when exposed to periodic forces at its natural frequency. Every object has a natural frequency, a rate at which it prefers to vibrate when disturbed. When an external force matches that frequency, the object absorbs energy more efficiently, causing its oscillations to grow. Over time, even small, repeated forces can build up into large, powerful vibrations. We see resonance everywhere. In music, when a guitar string is plucked, the vibrations are transferred to the soundboard, which resonates at the same frequency and amplifies the sound. In wind instruments, columns of air resonate to produce clear musical notes. It's resonance that gives instruments their tone and richness. But resonance can also be destructive. One of the most infamous examples is the Tacoma Narrows Bridge collapse in 1940. Strong winds happened to match the bridge's natural frequency, causing it to twist and sway violently until it tore itself apart. This event dramatically demonstrated the importance of designing structures that can withstand unintended resonant forces. In electronics, resonance enables precise control. LC circuits, made of inductors and capacitors, resonate at specific frequencies, and are used in radio tuning, filtering signals, and many communication technologies. In medical imaging, magnetic resonance, used in MRI scans, allows scientists to manipulate atomic nuclei with pinpoint accuracy using frequencies that match their natural spin behavior. Whether amplifying a musical note, enhancing the power of a circuit, or bringing down a bridge, resonance shows how powerful timing and frequency can be. When vibrations align perfectly with a system's natural rhythm, the result isn't just motion, it's magnified motion, a surge of energy made possible by the harmony of forces. Now, let's shift from vibration to something more steady and fundamental: pressure, the force that acts across surfaces and shapes the behavior of fluids, structures, and even the air around us. Every time you step on the ground, inflate a balloon, or dive underwater, you're experiencing pressure, a force that acts silently but powerfully across nearly every part of the physical world. Whether in the air, water, or deep beneath the earth, pressure is everywhere, governing how fluids behave, how objects interact, and how forces are transmitted. At its core, pressure is the amount of force applied per unit area. Imagine pressing your finger into your palm. It feels gentle. Now, apply that same force with a needle. Suddenly, it stings. The reason? The same force is concentrated over a much smaller area, increasing the pressure dramatically. This simple principle explains why knives cut, why high heels sink into soft ground, and why bullets pierce metal. In fluids, pressure behaves in unique and powerful ways. Pascal's principle states that in a confined fluid, pressure is transmitted equally in all directions. This principle is what makes hydraulic systems so effective. Apply a small force at one end of a system, and it's distributed to lift or move heavy loads. Car brakes, airplane landing gear, and construction equipment all rely on this fluid-based balance of pressure. In gases, pressure comes from molecular motion. Air molecules are constantly zipping around, colliding with surfaces, and in doing so, exerting force. Pump more air into a tire and you increase the number of molecules and their collisions, raising the pressure inside. This is why overinflated tires feel so rigid, and why weather balloons expand as they rise into thinner air. Atmospheric pressure is another everyday influence. At sea level, the weight of the air above us presses down with considerable force. But as you climb a mountain, there's less air above you, and thus less pressure. This explains why sealed bags puff up on airplanes, and why it becomes harder to breathe at high altitudes. From weather systems and aerodynamics to engineering and biological functions, understanding pressure allows us to explain how fluids and gases behave under different conditions. It's one of the most essential concepts in physics, an invisible force with visible impact, shaping the environment we live in. To see how pressure behaves when fluids are at rest, we move next into the realm of fluid statics, where forces balance and stability defines the system. Step into a swimming pool and descend slowly. As you sink deeper, you begin to feel a growing pressure pressing in on you from all sides. This quiet, invisible force is the realm of fluid statics, the study of how fluids at rest behave and the forces they exert, whether it's the weight of the ocean pressing down on a submarine, the buoyant force keeping a ship afloat, or the atmosphere resting gently on your shoulders. Fluid statics helps us understand the pressure and balance in fluids that aren't moving. One of the most important concepts in fluid statics is that pressure in a fluid increases with depth. This pressure acts in all directions, which is why when you're underwater, you feel it not just from above, but from the sides and below. It's also why dams are built thicker at the bottom. They must resist the increasing pressure from the water above. Interestingly, this pressure doesn't depend on the shape of the container. Only the depth, density of the fluid, and gravity matter. Another key principle is buoyancy, famously discovered by Archimedes. When an object is placed in a fluid, it experiences an upward force equal to the weight of the fluid it displaces. This is why a heavy steel ship can float. Its wide shape displaces enough water to match its weight, while a solid steel ball of the same material sinks. If the buoyant force exceeds an object's weight, it rises. If it's less, the object sinks. Fluid statics also brings us Pascal's principle. A change in pressure applied to a confined fluid is transmitted equally in all directions. This principle underlies hydraulic systems, where a small input force can lift a massive load, used in everything from car brakes and airplane landing gear to hydraulic lifts and construction machinery. From the balance that keeps hot air balloons aloft to the pressure systems that influence weather patterns. Fluid statics reveals the unseen architecture of stillness in our world. By mastering this field, scientists and engineers can harness the quiet strength of resting fluids, designing machines, structures, and vehicles that rely on balance, pressure, and buoyancy. But what happens when fluids are no longer still? When they move, swirl, and rush? That's the domain of fluid dynamics, where motion adds a new dimension to the power of fluids. From the lift beneath an airplane wing to the steady pulse of blood flowing through your veins, fluid dynamics is the science that explains how fluids move. Unlike fluid statics, which deals with still fluids, fluid dynamics explores motion, turbulence, and flow patterns, the dynamic side of water, air, and everything in between. One of the central concepts in fluid dynamics is the difference between streamlined flow and turbulent flow. In streamlined flow, also called laminar flow, fluids move in smooth parallel layers, like honey flowing gently through a tube or oil slipping down a glass wall. In contrast, turbulent flow is chaotic and unpredictable, filled with eddies, swirls, and vortices. Think of wind gusting around a corner or rapids crashing over rocks. Whether a fluid flows smoothly or turbulently depends on its speed, viscosity, and the shape of the surface it encounters. Another foundational principle is Bernoulli's principle, which states that as the speed of a fluid increases, its pressure decreases. This explains how airplanes achieve lift. Air flows faster over the curved top of the wing than underneath, creating a lower pressure above and pushing the wing upward. It's also the reason spray bottles work. Moving air lowers pressure and draws liquid upward into a fine mist. The continuity equation adds another layer to understanding flow. It tells us that the speed of a fluid must increase when it moves, through a narrower space. A river flows slowly where it's wide, but speeds up where it narrows. The same happens when water rushes through a small nozzle, or when blood flows through arteries narrower than veins. Fluid dynamics is everywhere. It governs weather systems, from swirling hurricanes to jet streams. It shapes vehicle design, ensuring that cars and airplanes move efficiently through air. It even powers medical advancements, from IV fluid delivery to heart valve performance. By understanding how fluids move, how they accelerate, twist, spread, or compress, engineers, scientists, and doctors can design better systems, predict natural phenomena, and improve technology that touches every part of life. And to understand the character of a fluid in motion, we turn next to one of its most defining traits: viscosity, a measure of how smoothly or sluggishly a fluid flows. Pour water into a glass and it flows easily, quick and smooth. Now try the same with honey. It stretches, oozes, and clings to the sides of the container. The difference? It's all about viscosity, a fluid's internal resistance to flow. Viscosity measures how much a fluid resists movement. Low viscosity fluids like water, air, or alcohol flow freely with little resistance. High viscosity fluids, like honey, syrup, or molten lava, move slowly and stickily, their molecules gripping each other as they move. This resistance comes from internal friction between molecules. In thicker fluids, molecules interact more strongly, making it harder for them to slide past one another. One of the key influencers of viscosity is temperature. When honey is heated, it flows much more easily. Its molecules move faster and don't stick together as tightly. The same principle explains why motor oil thickens in the cold, making engines harder to start in winter. That's why oil is engineered to perform across a range of temperatures, maintaining just the right balance between protection and flow. Viscosity also determines how objects move through fluids. Move your hand through water. It's easy. Try moving it through syrup, and suddenly you feel strong resistance. This is why aquatic animals like dolphins and penguins have evolved streamlined shapes to reduce the viscous drag of water and glide more efficiently. In industry, viscosity plays a crucial role. It affects how paint spreads, how ink prints, how medications are delivered, and how fuel flows through an engine. In the human body, even blood viscosity matters. It influences circulation, blood pressure, and how efficiently oxygen is delivered to tissues. Whether we're designing pipelines, mixing batter, treating illness, or just pouring maple syrup, viscosity governs the way fluids behave. It's the silent resistance inside every stream and swirl, shaping how substances move and how we move through them. And what drives much of this motion, interaction, and resistance? Temperature. It's the next concept that defines not just the feel of heat or cold, but the energy within matter itself. Touch a metal railing on a hot day. It stings. Grab an ice cube, and your fingers go numb. These sensations are all tied to temperature, the everyday measure of how hot or cold something feels. But beneath that simple feeling lies a deeper truth. Temperature is the measure of the average kinetic energy of particles in a substance. When particles move faster, they collide more often and more energetically. This increased motion raises the temperature. When they slow down, collisions become less intense and the temperature drops. So, temperature isn't about the size or mass of an object. It's about how energetically its particles are moving. To quantify this energy, we use several temperature scales. The Celsius scale, used worldwide, sets water's freezing point at 0 degrees and boiling point at 100 degrees. In the Fahrenheit scale, more common in the U.S., these points are 32 degrees and 212 degrees. Scientists, however, work with the Kelvin scale, where 0 Kelvin represents absolute zero, the point at which all molecular motion theoretically stops. Though often confused, temperature and heat are not the same. Temperature is a measure of motion at the particle level, while heat is the energy transferred between objects due to a temperature difference. A boiling cup of water may feel hotter than a tub of warm water, but the bathtub contains more total heat energy because it holds far more molecules, each with their own kinetic energy. Temperature influences everything. It drives weather systems, chemical reactions, and states of matter. In the freezing void of space, temperatures fall to unimaginable lows, while in the cores of stars, nuclear fusion pushes temperatures to millions of degrees, generating the light and heat that make life on Earth possible. Even our bodies rely on temperature control. A small shift, just a few degrees, can affect cellular processes, energy production, and survival. From cooking a meal to launching a spacecraft, Temperature is one of the most fundamental concepts we use to understand the behavior of matter and energy. And when that energy starts flowing from one object to another, we call it heat, a force in motion, and the next step in our journey through physics. It's what makes metal glow in a forge, water boil on a stove, and ice melt in your hand. Yet heat isn't a substance. It's the transfer of thermal energy from one place to another. At the atomic level, everything is always in motion. The faster the atoms and molecules move, the more energy they carry. And when two objects come into contact, that energy flows from the hotter one to the cooler one. This transfer, what we call heat, can happen in three fundamental ways: conduction, convection, and radiation. Conduction is the simplest. It's heat transferred through direct contact. Touch a hot pan, and energy rushes from the metal into your skin. That happens because fast-moving particles in the pan collide with slower particles in your hand, sharing their energy. Materials like metals are excellent conductors because their atoms are tightly packed and allow energy to move easily through them. Convection occurs in fluids, liquids, and gases. As these materials heat up, warmer, less dense regions rise while cooler, denser regions sink. This creates a cycling flow of energy. It's how water circulates in a pot, how air currents shape weather, and how heat travels inside the Earth. Radiation is entirely different. It doesn't need a medium at all. Energy travels as electromagnetic waves, like the rays from the sun that warm the Earth or the heat you feel standing near a fire. Even across the vacuum of space, radiation carries energy swiftly and invisibly. While temperature tells us how energetic particles are on average. Heat measures the total energy transferred. A tiny spark from a match may be very hot, but it holds far less total heat energy than a cup of warm water, simply because it contains far fewer particles. Heat is more than just something we feel. It shapes the planet and powers life. It drives weather systems, fuels engines, and sustains the conditions we need to survive. From the warmth of a campfire to the energy behind a nuclear reactor, understanding heat gives us control over energy in motion, making it one of the most vital concepts in both science and daily life. But what happens when heat flows, or doesn't, between objects? That brings us to the foundation of thermal physics, the Zeroth Law of Thermodynamics, which helps define what it truly means for something to be in thermal equilibrium. Pour hot coffee into a cold mug. At first, the coffee cools slightly and the mug warms up. Wait a few minutes and both reach the same temperature. They've come into thermal equilibrium. This everyday experience reveals one of the most deceptively simple but absolutely foundational laws of physics, the Zeroth Law of Thermodynamics. The law states, if two systems are each in thermal equilibrium with a third system, then they are also in thermal equilibrium with each other. Put simply, if object A is the same temperature as object C, and object B is also the same temperature as object C, then A and B must be the same temperature too. It sounds obvious, but this relationship gives temperature a clear, measurable meaning, allowing us to define and compare it with confidence. Consider how this applies to a thermometer. When it's placed in contact with another object, like your forehead or a pot of soup, the thermometer adjusts its own internal energy until it matches the object's temperature. Thanks to the Zeroth Law, we know that when both the thermometer and the object stop exchanging heat, when they're in equilibrium, they must be at the same temperature. That's how we can trust the reading. Without this law, There would be no consistent way to define or compare temperature. Thermometers wouldn't work, thermostats wouldn't regulate, and much of thermodynamics wouldn't function. This principle gives us the concept of temperature itself, the idea that it's a real, quantifiable state that can be shared between systems. Though named the Zeroth Law, only after the first, second, and third laws had been established, it underpins them all. It's the reason heat flows from hot to cold, why engines can be designed to use temperature differences, and why we understand how energy spreads. In its quiet simplicity, the Zeroth Law is the starting point of thermal science, the invisible, logic behind everything from climate control to cooking. And building on this equilibrium, the first law of thermodynamics takes us deeper into how energy behaves, transforms, and is forever conserved. Strike a match, drink a hot cup of tea, start your car, or even take a breath. Energy is everywhere, flowing from one form to another. And yet, despite all the movement and change, one thing remains constant. The total amount of energy never changes. This is the essence of the first law of thermodynamics, a law so fundamental that it shapes every process in the universe. The first law states that energy cannot be created or destroyed. It can only be transferred or transformed. In more technical terms, the total energy of an isolated system remains constant over time. Think of a cup of hot tea left on the table. As time passes, the tea cools. But where does that heat go? It doesn't vanish. It transfers into the surrounding air, warming nearby molecules. The energy is conserved, merely moving from the liquid to the atmosphere. Or take your body. When you eat, you absorb chemical energy from food. That energy transforms into kinetic energy when you move, thermal energy to maintain body temperature, and electrical energy to power your nervous system. The total energy stays the same. It just changes form. This law is also what powers engines. In a car, chemical energy from burning fuel becomes heat energy, which is then used to create mechanical work, moving the pistons and propelling the vehicle forward. Not all of that energy becomes useful work, though. Some is always lost as waste heat, which is why no machine is perfectly efficient. The first law governs everything from metabolism in your cells to the fusion reactions inside stars, from your microwave oven to entire power plants. Every action, every transformation, every energy exchange follows this rule. It's a universal reminder. Energy never just disappears. It only moves, shifts, or transforms. It may leave one place and appear in another, or change form from light to heat or motion to sound, but it's always accounted for. And while the first law tells us energy is preserved, the second law of thermodynamics adds a powerful twist. It reveals the direction in which energy flows and the reason why disorder, or entropy, always increases. Ice melts, batteries drain, and hot coffee cools. Machines heat up and lose efficiency. Stars shine brilliantly and then fade. All of these natural events have something in common. They follow the second law of thermodynamics, a law that doesn't just govern energy, but the very direction of time and the fate of the universe. At its core, the second law states that in any energy transfer or transformation, the total entropy of a system and its surroundings will always increase. In other words, while energy is conserved, as the first law tells us, it becomes less organized, less useful, and more spread out over time. But what is entropy? It's a measure of disorder or randomness in a system. A stack of books neatly arranged on a shelf has low entropy. It's organized and structured. Knock them over and the pile becomes chaotic and disordered. High entropy. The second law says that nature tends to move from order to disorder unless energy is continuously used to maintain or restore structure. This is why heat always flows from hot to cold, never the other way around. Leave a cup of hot coffee in a cool room, and the warmth spreads out into the air. That heat will never spontaneously gather itself back into the cup. This flow of heat, this one-way street, defines the natural progression of time. The law, also, explains why no machine is perfectly efficient. Every engine, motor, or electronic device loses some energy as waste heat to its surroundings. This energy is still there. It hasn't vanished, but it's now too disorganized to do useful work. Even life itself defies entropy only by constantly consuming energy, food, sunlight, fuel, to maintain structure. On a cosmic scale, the second law paints a sobering picture. As stars burn their fuel and galaxies evolve, the universe trends toward maximum entropy, a state where all energy is evenly distributed and no more work can be done. This theoretical fate is called the heat death of the universe, a silent, motionless state of complete equilibrium. Yet within that ever-increasing disorder, life and technology carve out moments of order. We build, we power, we create, but always at a cost, always pushing against the tide of entropy. And while the second law reveals the inevitable spread of energy, the third law of thermodynamics explores the limit of what happens when there's almost no energy left to spread at all, when everything approaches absolute zero. Picture a world where nothing moves. No vibration, no sound, not even the twitch of an atom. This is the realm imagined by the third law of thermodynamics, which explores what happens when matter reaches the edge of absolute stillness. The law states, as a system approaches absolute zero, the lowest possible temperature, its entropy, or disorder, also approaches a minimum value. Absolute zero is 0 Kelvin, or 273.15 degrees Celsius. At this theoretical temperature, all molecular motion would stop completely. No jiggling atoms, no vibrations, just perfect silent order. As a material cools, its particles slow down. Their energy fades and they begin to settle into more predictable, structured arrangements. In theory, a perfect crystal, with no impurities, defects, or irregularities, would have zero entropy at absolute zero, because there's no randomness left in how its atoms are arranged. But here's the catch. We can never actually reach absolute zero. No matter how powerful our technology becomes, we can only approach it, getting ever closer without fully arriving. Why? Because removing that final shred of heat, the last tiny flicker of energy, would require an infinite amount of work. Yet this extreme limit isn't just theory. It's had real, revolutionary applications. As substances are cooled to near absolute zero, they begin to behave in extraordinary ways. For instance, some materials lose all electrical resistance, becoming superconductors, a property harnessed in MRI machines, magnetic levitation trains, and quantum computers. The third law sets a definitive lower boundary in physics. It tells us not just how cold things can get, but also how ordered systems can become. In a universe defined by entropy and decay, it offers a final, unreachable promise, a perfect state of structure, frozen in stillness. As we venture from these fundamental thermodynamic principles into the behavior of gases, we encounter the ideal gas law, a powerful equation that ties together pressure, volume, temperature, and quantity, describing how gases behave in the real world and in the lab. Gases often behave as though they're unpredictable, expanding to fill any available space, compressing under pressure, and weaving through even the tiniest openings. Yet, beneath this apparent chaos is a striking simplicity captured by the ideal gas law, one of the most essential tools in physics for decoding the behavior of gases. This law reveals how 4 key properties, pressure, volume, temperature, and particle count, are all interlinked. If you change one, the others must respond in kind to keep the system in balance. Heat a gas and its particles speed up, increasing. Pressure, unless you also expand the volume to give them more space. Compress the gas and pressure rises. Cool it and the particles slow down, reducing both volume and pressure. This dance between properties explains common experiences: why balloons deflate in the cold, why sealed containers can burst in heat, and how your lungs adjust with every breath. Represented mathematically as PV, Q, nRT, the ideal gas law expresses these relationships clearly. Pressure, P, multiplied by volume, V, equals the number of moles of gas, N, times a constant, R, and temperature, T, in Kelvin. While it assumes ideal conditions, such as gas particles that don't interact and occupy no volume, it still proves remarkably accurate for everyday scenarios, especially under standard temperature and pressure. Its applications span from car, engines and weather balloons to airplane cabin systems and medical devices. It even helps scientists model the behavior of gases in deep-sea environments and the vacuum of space. More than just an equation, the ideal gas law serves as a framework for revealing the hidden structure in the seemingly random world of gases. And to truly understand why this law works so well, we journey next into the microscopic world of the kinetic theory of gases, where motion, collisions, and molecular chaos become the key to the bigger picture. At first glance, a gas may seem like a formless floating cloud, but if we could zoom in to the molecular level, we'd witness a world of frantic motion. Countless invisible particles, atoms or molecules, rush in every direction, bouncing off each other and the walls of their container in an endless chaotic dance. This is the realm described by the kinetic theory of gases, a fundamental model that explains how gases behave by focusing on the constant motion of their particles. According to this theory, gas particles are in perpetual, random motion. They travel in straight lines until they collide, either with one another or with the surfaces around them. Each of these microscopic impacts exerts a force, and the collective effect of billions of such collisions is what we recognize as pressure. The faster and more frequent the collisions, the higher the pressure. And what controls this speed? Temperature. As the gas heats up, its particles move faster, increasing pressure. If the gas is free to expand, the added energy also increases. Its volume. Cool the gas and everything slows. The collisions become gentler and less frequent, lowering both temperature and pressure. This motion explains another familiar gas behavior: compressibility. Because gas particles are widely spaced compared to solids and liquids, most of the volume in a gas is simply empty space. That means gases can be compressed easily, particles are pushed closer together, or allowed to expand into more space when pressure drops. This is why air can be pumped into tires, why balloons inflate, and how pressurized cabins on airplanes protect passengers high above Earth. But the kinetic theory isn't just a thought experiment. It's a critical tool across science and engineering. From predicting weather patterns and designing spacecraft life support systems to fine-tuning engines and understanding explosions, it provides the microscopic lens needed to see how energy, temperature, and motion are interconnected. Through it, we learn that even in the apparent disorder of gases, there is a deep and predictable structure. Next, we turn to what happens when substances shift between states of matter, a process filled with mystery and transformation. Phase transitions. Ice melts, water boils, steam condenses. These everyday events are more than simple transformations. They are vivid expressions of one of the most important concepts in physics, phase transitions. At their core, phase transitions describe how matter shifts between solid, liquid, and gas states, all governed by temperature, pressure, and energy. But while the process may appear straightforward, what happens at the molecular level is a powerful demonstration of how energy drives change. Matter is made up of molecules in constant motion. In a solid, these molecules are tightly packed, vibrating in fixed positions within a rigid structure. Add heat, and they begin to vibrate more intensely. Eventually, they gain enough energy to break free from their fixed bonds, melting the solid into a liquid. In this new state, the molecules are more mobile, able to slide past one another while still held loosely together. As heat continues to rise, the molecules eventually gain enough energy to completely escape the liquid's surface, evaporating into a gas. In the opposite direction, removing energy causes a gas to cool and slow, with molecules clustering back into a liquid, condensation, or further into a rigid solid, freezing. But phase transitions don't stop there. Under extreme conditions, matter behaves in extraordinary ways. Plasma, the fourth state of matter, emerges when atoms are stripped of their electrons, leaving behind a soup of charged particles. This state is found in stars, lightning, and neon signs. On the other end of the energy spectrum lies the exotic Bose-Einstein condensate, where atoms near absolute zero slow down so much they begin to act as one single quantum entity, a phenomenon that challenges our classical understanding of matter entirely. Phase transitions aren't just scientific curiosities, they are everywhere. They drive weather patterns through the water cycle, enable technologies like refrigeration, and play a central role in metallurgy, materials science, and even quantum research. By studying these transitions, we gain insight into how energy, structure, and temperature interact to reshape matter itself, reminding us that every shift in form reveals a deeper story about the forces that govern our universe. Next, we move from these transformations into a new domain of physical behavior, the study of balance, support, and equilibrium. Statics. What keeps a towering skyscraper upright during a storm? How does a ladder lean against a wall without slipping? What holds a suspension bridge in place, gracefully suspended above a river? The answer lies in statics, a branch of physics dedicated to understanding forces in balance. It's the silent guardian of stability, ensuring that structures, objects, and systems remain at rest or move steadily without change. At the heart of statics is equilibrium. According to Newton's first law, an object will remain at rest, or in uniform motion, unless acted upon by an unbalanced force. In static situations, all forces and torques acting on a body must cancel out perfectly. This balance is what allows buildings to stand, bridges to span gaps, and even a pile of books to rest neatly on a table without collapsing. Statics considers two essential conditions for this balance: translational equilibrium and rotational equilibrium. Translational equilibrium occurs when all the forces acting on an object sum to zero, meaning there's no net movement in any direction. Rotational equilibrium, on the other hand, ensures that all torques, rotational forces, also sum to zero, preventing the object from spinning or tipping over. Picture a seesaw with two kids of equal weight sitting at equal distances from the center. It stays level because both the linear forces and rotational effects are perfectly balanced. These concepts are not abstract. They are applied in architecture, engineering, and design every day. Architects use statics to design buildings that can handle wind loads and structural stress. Engineers rely on it to build cranes, dams, and towers that don't tip or buckle. Even setting up scaffolding or stacking dishes in a cupboard draws on principles of statics, consciously or not. Understanding statics is about mastering the interplay of forces in stillness. It's the reason bridges don't collapse under traffic, ladders don't fall when leaned correctly, and buildings resist the pull of gravity and time. In a universe constantly in motion, statics is the science that makes stillness possible, providing the foundation for stability in both natural and human-made worlds. Next, we shift from the large and immobile to the invisible and unpredictable, into the realm of statistical mechanics, where the behavior of countless particles gives rise to the laws of thermodynamics. Imagine trying to track every molecule in a gust of wind, all moving at different speeds in random directions, constantly colliding. It sounds like an impossible task. And yet, from this chaos, emerges something beautifully predictable: temperature, pressure, entropy. That's the power of statistical mechanics, a branch of physics that bridges the chaotic motion of countless microscopic particles with the orderly laws that govern the macroscopic world. While classical mechanics focuses on the motion of individual objects, planets, pendulums, or projectiles, statistical mechanics deals with systems made up of trillions upon trillions of particles. Instead of tracking each one, it relies on probability to understand the average behavior of the whole. It's like watching the tide roll in rather than studying every single water droplet. One of the most profound insights from statistical mechanics is the true meaning of temperature. It's not tied to a single molecule, but to the average kinetic energy of all the molecules in a system. Faster movement means higher energy and therefore higher temperature. Similarly, pressure isn't the result of a single collision. It's the collective force of billions of molecules striking the walls of a container. Then comes entropy, a concept often misunderstood as mere disorder. In statistical mechanics, entropy is a measure of the number of microscopic configurations that correspond to a system's macroscopic state. The more possible arrangements, the higher the entropy. That's why heat flows from hot to cold, why gases spread out, and why time seems to move forward, because the probability favors disorder. Statistical mechanics also unlocks the secrets behind phase transitions. When ice melts, it's not just a physical change, it's a massive shift in how molecules behave, moving from an ordered structure to a more random state. The same applies to water boiling, magnets losing alignment, and materials becoming superconductive. Behind each transition is a delicate dance of probabilities. This framework even extends into quantum mechanics, where it predicts how electrons distribute themselves in atoms, how particles behave at near absolute zero, and how entire materials respond to energy and temperature. In essence, statistical mechanics takes the invisible chaos of the microscopic world and reveals the invisible order behind it. It shows us that while we may never track every molecule, we can still understand the universe they create, one probability at a time. Up next, we shift from the probabilistic world of particles to the charged fabric of matter itself with electric charge, the source of one of nature's most powerful and dynamic forces. Flip a switch, plug in your phone, or feel a static jolt when touching a doorknob, and you've just encountered one of nature's most powerful properties, electric charge. Though invisible to the eye, electric charge lies at the heart of everything, from your morning coffee maker to the structure of atoms and the fury of thunderstorms. Electric charge is an intrinsic property of matter, meaning it's built into the very particles that make up the universe. It comes in two types, positive and negative. Opposite charges attract, like charges repel. This simple yet profound rule is the basis of all electromagnetic interactions. At the atomic level, protons carry positive charge, electrons carry negative charge, and neutrons remain neutral. Most. Matter is electrically neutral overall because it contains equal numbers of positive and negative charges. But when there's an imbalance, when electrons are gained or lost, forces come into play. That's what's happening when you rub a balloon against your hair. The balloon steals electrons, becoming negatively charged, while your hair loses electrons and becomes positively charged. The result? Attraction. The balloon clings to the wall or to your hair, held in place by invisible electric forces. Electric charge is measured in coulombs, a unit named after Charles-Augustin de Coulomb, who mathematically described how charged objects interact. His work showed that the force between two charges depends on both their magnitude and the distance between them, a relationship that would become a foundation for understanding electrostatics. But charge isn't just a static property. It flows. When charges move, especially electrons, they generate electric currents. This flow of charge is what powers circuits, lights homes, runs computers, and drives motors. It's the pulse of modern life. Even nature relies on electric charge. Lightning is the dramatic discharge between regions of opposite charge in clouds and the ground. And inside your body, tiny electrical signals carried by charged ions allow your brain to communicate with your muscles and organs. Electric charge is more than just a scientific term. It's the invisible thread running through technology, chemistry, biology, and physics. It binds atoms, powers cities, and shapes the very structure of reality. And to understand how these charges influence one another at a distance, we now turn to a precise mathematical tool, Coulomb's law, a law that reveals the force behind every electric interaction. Every spark, every static shock, every charged particle in the universe follows one simple, powerful rule, Coulomb's law. Named after French physicist Charles-Augustin de Coulomb, this principle describes how electric charges interact with one another. Though the charges themselves are invisible, the forces they create can be felt, seen, and precisely calculated. At its core, Coulomb's law states that the force between two electric charges depends on two things: the amount of charge on each object and the distance between them. The greater the charge, the stronger the force. But the farther apart the charges are, the weaker the force becomes. Specifically, it decreases with the square of the distance. If you double the distance, the force becomes 4 times weaker. This inverse square relationship is also seen in gravity, showing just how deeply this pattern is woven into the laws of nature. To visualize it, imagine 2 small charged objects, like static-filled balloons. When held close together, they either repel or attract with noticeable strength. Move them apart, and that invisible tug or push quickly fades. This isn't just a quirky trick of everyday physics, it's the exact mathematical rule followed by every pair of charged particles in the universe. Coulomb's law doesn't just explain how objects like socks stick together after a tumble in the dryer. It lays the foundation for understanding atomic structure, showing why negatively charged electrons stay bound to positively charged nuclei. It explains how chemical bonds form, how ionized particles behave in plasma, and how capacitors store energy in circuits. The force described by Coulomb's law is a vector. It has both magnitude and direction. It can pull or push depending on the signs of the charges involved. Opposites attract, likes repel, and while gravity only attracts, electric force can do both, making it far more dynamic in how it shapes matter and motion. This law is essential in fields ranging from electronics and chemistry to astrophysics. Whether you're designing microchips, studying molecules, or modeling the plasma jets of distant galaxies, Coulomb's law gives you the blueprint to understand and predict electrostatic behavior with precision. It's not just about particles and equations. It's a reminder that hidden beneath every electric interaction is an elegant, invisible force, pulling the universe together or pushing it apart. And to truly understand how this force acts through space, we must now explore what it creates around every charge, the electric field. Imagine holding a balloon rubbed against your hair. You feel a faint tug, maybe even a spark, but the balloon never touches anything. That invisible pull is caused by something real and powerful, an electric field. An electric field is the invisible region of influence surrounding any object with an electric charge. It reaches across space, affecting other charges nearby without needing physical contact. Just as gravity pulls objects toward Earth without a rope or connection, electric fields exert forces between charges, silently, instantly, and predictably. Created. By every charged particle, the electric field extends outward like an unseen aura. A positive charge produces a field that pushes outward in all directions, while a negative charge pulls inward. If you place another charge within that field, it will feel a force. The direction and strength of this force depend on the electric field at that point and the nature of the charge placed within it. The closer you get to the source charge, the stronger the field becomes. Move farther away, and the field weakens with the square of the distance. To picture it, imagine placing a marble on a tilted surface. The marble rolls because of gravity, guided by the slope. Similarly, charges roll through electric fields, only instead of hills and valleys, the landscape is shaped by electric forces. Electric fields aren't just theoretical. They play out in real-world phenomena every second. Lightning bolts strike when electric fields between the clouds and ground grow strong enough to break down air molecules. Your phone's touchscreen works by detecting how your finger disturbs an electric field on the screen. Even your nervous system uses electric fields, tiny ones, to transmit signals between brain, muscles, and organs. When multiple charges are near each other, their fields interact and create complex patterns like overlapping ripples in water. These patterns guide the motion of charged particles and influence how forces are distributed through space. Understanding electric fields gives us the power to manipulate electricity, build advanced technologies, and predict how charged particles behave, from the inner workings of atoms to the dynamics of solar flares. It's the backbone of electrostatics and one of the most important tools in physics, an unseen scaffold that shapes the behavior of the visible world. But what drives charges to move through these fields? What gives them the potential to act? To understand that, we must turn to the concept of electric potential, the hidden energy waiting to be unleashed. Electric potential is the silent architect behind every flicker of light, every spark, every surge of power. It's what makes charges move, what gives electric fields their power to do work, and what ultimately drives the entire flow of electricity. If an electric field is the landscape, then electric potential is the elevation, guiding charges like gravity guides falling water. At its essence, electric potential represents the amount of potential energy per unit charge at a specific point in space. The higher the potential, the more energy is available to a charge placed there. Just as a ball perched at the top of a hill has the capacity to roll downward due to gravity, a positive electric charge placed in a region of high potential has the capacity to move, falling through the electric field to a region of lower potential. To grasp this intuitively, think of a waterfall. Water at the top has more gravitational potential energy than at the bottom. When it falls, that energy turns into motion. In the same way, charges fall from high electric potential to low, and this movement generates electric current. The difference in electric potential between 2 points is what we call voltage. It's the push that powers your phone, your home, your city. When you plug in a device, you're tapping into this difference, allowing electrons to move through wires, lighting up screens, turning motors, and fueling computation. The higher the voltage, the greater the push on charges, and the more energy delivered per unit charge. Electric potential isn't limited to man-made systems. It governs natural phenomena too. Lightning occurs when the electric potential between a cloud and the ground becomes so large that it overcomes air's resistance, unleashing a dramatic transfer of energy. Inside your body, neurons use tiny voltage differences across membranes to send signals that control everything from thoughts to muscle movements. Understanding electric potential is crucial not just for using electricity, but for mastering how it flows. It's what powers circuits, ignites chemical reactions in batteries, and underpins every electronic device in our world. And when we want to store that energy, to save it for the perfect moment, we turn to capacitance. The next step in mastering electricity. Capacitance is the quiet power behind some of the most familiar technologies around us. Camera flashes, audio systems, electric cars, and even the memory in our computers. At its core, capacitance is the ability to store electric charge. But more than just storage, it's about storing energy efficiently and being ready to release it in an instant when needed. The device that brings this concept to life is the capacitor. Simple in design, a capacitor consists of two conductive plates separated by an insulating material called a dielectric. When connected to a voltage source, electrons build up on one plate, while the other loses electrons and becomes positively charged. This separation of charge creates an electric field between the plates, and with it, the ability to store energy. Picture it like a water tank with a flexible membrane in the middle. As water fills one side, the other side stretches outward. The tension in the membrane represents stored energy, waiting to be released when needed. In the case of a capacitor, that release is a sudden flow of electricity, a burst of power with precise control. How much a capacitor can hold, its capacitance, depends on a few factors: the size of the plates, the distance between them, and the nature of the dielectric. Larger plates mean more space to hold charge. Plates placed closer together intensify the electric field, increasing storage. And certain dielectric materials can significantly boost a capacitor's ability to store energy. Unlike batteries, which release energy slowly over time, capacitors charge and discharge almost instantly. This makes them perfect for handling quick energy spikes or drops. They're used to smooth out voltage in power supplies, filter noise in audio circuits, and deliver rapid energy in electric vehicles and camera flashes. In modern technology, capacitors are everywhere, managing energy with silent precision. They're the reason your speakers sound clean, your computer boots quickly, and your phone survives momentary power dips. To truly understand how electric circuits behave, how they resist, carry, and respond to electrical energy, we need one more tool: Ohm's law. It's the next piece in unlocking how current, voltage, and resistance come together to define the flow of electricity. Every time you flip a switch, charge your phone, or power on your laptop, you're witnessing one of the most essential forces in modern life: electric current. It's the steady stream of charged particles, usually electrons, moving through a conductor like copper wire. Just as water flows through pipes from high pressure to low pressure, electric current flows from high electric potential to low. What pushes this current? Voltage, the electrical pressure that drives charges forward. But there's always something that resists this motion: resistance. The interplay between these three, voltage, V, current, I, and resistance, R, is captured beautifully by Ohm's law, one of the most important relationships in physics. Ohm's law states current equals voltage divided by resistance. In other words, if you increase the voltage and keep resistance constant, more current flows. But if you increase the resistance while holding voltage steady, the current drops. Picture a water hose. Turn up the faucet, voltage, and more water, current flows. But if the hose gets pinched, resistance, less water gets through. Electricity works the same way. This simple law governs every circuit you encounter. It tells engineers how to design circuits that don't overheat, ensures your phone doesn't short-circuit when charging, and allows household appliances to operate safely. Resistors, for instance, are key components that intentionally reduce current, protecting sensitive electronics. Circuit breakers monitor current levels and cut the flow when it gets too high, preventing fires or damage. From light bulbs glowing at just the right brightness to electric cars delivering safe and efficient power, Ohm's law is at work behind the scenes. It's not just a formula. It's a tool that brings control to the invisible world of flowing charges, making electricity usable, predictable, and safe. As we dive into basic circuit analysis next, we'll see how these concepts come together. How resistors, voltage sources, and current paths interact to form the backbone of every electronic system we use today. Electricity powers everything around us, from the smallest flashlight to complex supercomputers. To understand how electricity flows, it's essential to comprehend how circuits work. Circuit analysis is the method used to study how voltage, current, and resistance interact within a circuit. A basic circuit is composed of three core components: the voltage source, which provides the push needed for electrons to move, such as a battery; resistors, which limit the flow of current, much like narrowing a water pipe; and conductors, the wires that carry electricity between components, similar to roads guiding traffic. The behavior of electric circuits is governed by two primary laws. Ohm's law relates voltage, current, and resistance. It helps us understand how much current will flow through a component based on the applied voltage and its resistance. Kirchhoff's laws are applied when analyzing circuits with multiple loops and branches. Kirchhoff's voltage law states that the sum of voltages around any closed loop must equal zero, ensuring energy is conserved. Kirchhoff's current law dictates that the total current entering a junction must equal the total current leaving, much like cars merging into lanes on a highway. By applying these laws, engineers can calculate how current and voltage are distributed across complex circuits, ensuring proper function and safety. This analysis is crucial in designing everything from household wiring to microprocessors. Understanding how circuits work is essential, because circuits form the foundation of modern technology. They allow us to harness electricity efficiently and ensure that devices operate as intended. A magnetic field is an invisible force field created by moving electric charges or magnetic materials. It surrounds magnets and electric currents, shaping how magnetic objects interact even without touching. Imagine holding a magnet near iron filings. They align into clear, curved patterns, outlining the magnetic field's presence and shape. This field extends outward from the magnet's poles, looping from the North Pole to the South Pole outside the magnet, and continuing from south to north within it, forming continuous loops. The strength of the magnetic field decreases rapidly as you move farther away, just like light from a candle dimming with distance. But magnetic fields aren't only about permanent magnets. Electric currents produce them too. When electric current flows through a wire, it creates a circular magnetic field around the conductor, forming the basis for electromagnets. Electromagnets are powerful because their fields can be easily switched on, off, or reversed by adjusting the electric current. This controllability is crucial in countless applications, from motors and generators to MRI machines and magnetic levitation trains. Magnetic fields also protect our planet. Earth's core generates a magnetic field that shields us from harmful solar radiation by deflecting charged particles, enabling life to thrive. This invisible shield creates stunning natural phenomena, such as the northern lights. Understanding magnetic fields is vital to modern technology. They enable data storage, wireless charging, navigation compasses, and even advanced medical imaging. In essence, magnetic fields quietly shape our lives and the technology we depend upon, influencing everything from the smallest electronic devices to the vastness of space itself. A compass needle gently swings northward, guiding travelers safely home. Bright green auroras dance across the night sky, painting the heavens with mysterious beauty. A magnet effortlessly picks up metal, defying gravity itself. Behind each of these wonders lies an invisible yet powerful presence: the magnetic field. At its core, a magnetic field is an unseen region surrounding magnets and electric currents, influencing objects without ever making contact. It's like an invisible ocean of force stretching out from one magnetic pole to the other, guiding magnetic materials along clearly defined paths. Sprinkle iron filings around a bar magnet, and suddenly this hidden force springs vividly to life. the filings lining up into beautiful loops, tracing the invisible magnetic pathways. But magnetic fields are far more than just the domain of classroom experiments. Our entire planet is wrapped in one, Earth's magnetic field, generated deep within its molten iron core. This magnetic shield deflects dangerous solar radiation, protecting all life on Earth. Without it, our atmosphere could vanish, and the planet would become barren, lifeless, and exposed to cosmic storms. Magnetic fields don't just defend, they empower technology too. Pass an electric current through a coil of wire, and you'll instantly create your own controllable magnetic field, an electromagnet. This simple phenomenon underpins countless innovations, from electric motors spinning tirelessly in appliances and cars, to transformers smoothly managing our power supply, and even the magnetic resonance imaging (MRI) machines that peer deep inside our bodies. Beyond Earth, magnetic fields sculpt cosmic landscapes, influencing stars, galaxies, and nebulae. They guide charged particles from the sun into brilliant displays like the northern lights and shape the environments of distant planets, creating invisible highways through the vastness of space. Understanding magnetic fields means mastering the unseen forces that shape our universe, from the simplest compass needle to the grandest cosmic spectacle. They quietly guide, protect, and power the world around us, proving that even the most invisible forces can have the most profound effects. Imagine harnessing motion itself, turning the spin of a turbine, the movement of a magnet, or even the rush of water into electrical power that lights cities, charges phones, and powers entire civilizations. This astonishing transformation is, at the heart of electromagnetic induction, one of the greatest discoveries in physics. Electromagnetic induction occurs when a changing magnetic field generates an electric current in a conductor. Discovered in 1831 by Michael Faraday, this phenomenon revealed the incredible connection between electricity and magnetism. Faraday noticed something remarkable. Moving a magnet through a coil of wire caused a sudden flow of electricity. The key was not just the magnet or the wire, but the motion itself. A static magnet had no effect, but the instant it moved, electricity flowed. Picture a coil of wire resting quietly in a magnetic field. Nothing special happens. Now, swiftly move the magnet closer, and suddenly electrons within the wire spring to life, flowing in response to the changing magnetic field. This seemingly magical process is precisely described by Faraday's law, which states that the voltage induced in a circuit depends directly on how quickly the magnetic field changes and how many loops of wire it passes through. Faster motion, stronger magnetism, or more loops, all of these amplify the electricity generated. This simple yet powerful insight revolutionized technology. Generators at power plants rely on induction, spinning massive coils within magnetic fields to supply electricity to entire regions. Transformers, crucial to delivering electricity efficiently across vast distances, depend on this same principle, effortlessly adjusting voltage levels to match our needs. But electromagnetic induction is more than just a practical discovery. It's a gateway into understanding the profound relationship between electricity and magnetism. It's the principle behind nearly every modern convenience, from the humming turbines that power our homes to the intricate circuits that charge our phones. Faraday's discovery of induction forever changed how humanity uses energy, bridging motion, and electricity in ways he could scarcely have imagined. What if, centuries from now, we discover even deeper connections, new hidden forces waiting to be harnessed, inspired again by Faraday's timeless insight into the elegant interplay of electricity. And magnetism,